Hello, everybody, and welcome to this introductory course on blockchain development and Solidity. Throughout this course, not only will you learn about theoretical concepts related to blockchain networks like Ethereum, but you will understand how to write smart contracts in Solidity, how to deploy those onto the Ethereum network, and how to do things like create ERC20 and ERC721 tokens, which are NFTs. This course is designed for complete beginners. Whether you have experience with blockchain or programming or not, you will be able to follow along with this content. Now, this content is meant to just be a good introduction to this topic and to this space. This is not going to teach you everything you need to know to become a Web3 developer, but it's going to be a really good starting place and kind of show you if you're interested in this or not. So after going through this course, if you are interested in Web3 technology, you really want to get to the next level, you want to potentially land a job, I have an entire premium course. It's called Blockchain Expert. I'll leave a link to it in the description. This covers some of the same content as this introductory course, but obviously it goes much more in depth. We have over 20 hours of video content. We have full projects using things like oracles. We show you how to actually write front-end code that can interact with your smart contracts. We teach you advanced Solidity features. There's hundreds of practice questions, assessment questions, projects, so much more. It's a great value. You guys can check that out from the link in the description. Now, this course is an aggregation of a bunch of videos I made about a year ago. I know many of you don't actually know that I have these videos, so every once in a while I like to combine them all together. So you're going to see that after this intro, there's kind of another intro, and then it goes through all of the videos that I posted on the channel a really long time ago. So just keep that in mind. This is kind of an aggregation, and I wanted to give you this introduction just so you understand the purpose of this course. And I also wanted to mention that it's possible that when you try to use what's known as the Gorelli test network, this is a network we used in this course about a year ago, it will fail. Now, if that fails, I've left a link in the description to another test network that you can use. It's called Avalanche, so use that test network instead. The setup steps are essentially the same, except instead of connecting to Gorelli, you connect to Avalanche. So you may have to do a quick Google search, how to connect to the Avalanche test network. It's fine. I've left a link to the faucet. A faucet is a place where you can get kind of free Ethereum, so you can actually test out your smart contracts. So hopefully you guys can keep that in mind. I apologize if the network doesn't work. I don't have any control over that, but I've left an alternative, so hopefully you can kind of continue in this course without any issues. With that said, I hope you guys are looking forward to this. All of the resources for all of the videos will be linked in the description, as well as the link to Blockchain Expert. Let's get into the first video and dive into blockchain development. Hello everybody, and welcome to a brand new and very exciting series on this channel on an introduction to blockchain development. So in this series, I'm going to be showing you how to write smart contracts and deploy them on the Ethereum network. And I just want to state before I go any further, this is designed for complete beginners. So if you have never written code before, if you don't know anything about blockchain, do not worry, this is the place for you. I'm going to be explaining absolutely everything. And in this series, we're not going to write any massively complicated smart contracts. This is really meant to give you kind of a high-speed introduction and just get your hands dirty and actually deploying and writing contracts. Anyways, with that said, in this first video here, what I'm going to be doing is showing you how to set up Ethereum. So how to set up a wallet, how to get some different accounts, and then how you can get free Ethereum from an Ethereum test network. This is important because when we're kind of practicing, we don't want to be spending real money, and you do need to actually spend Ethereum to put your smart contracts on the Ethereum network. So I'll show you how we can do that for free in this video. So I'm super excited for this series. I hope you guys are as well, and there will likely be more on blockchain related topics on this channel coming in the future, so look forward to that. Now, I do need to mention, and I apologize for the long intro here, that the reason why I'm able to actually create this series is because of a company known as Cartesi. Now, Cartesi is the sponsor of this video and this series, and they've actually been working with me behind the scenes to come up with the curriculum here and make sure that I'm getting everything correct as I'm relaying this information to you. I am not a blockchain expert. I am kind of a beginner just like you guys, but I am good at making YouTube videos and tutorials, and so they've been kind of helping me come up with the content in the structure and then reviewing all of the work just to make sure everything is 100% accurate. Now, Cartesi is an amazing company. They're dedicated to making the blockchain more accessible for everyone, and they have a ton of technology solutions that allow you to develop on the blockchain for much cheaper. Now, we will hear more about them throughout the rest of this series, but for now, I just wanted to give them a general introduction and a massive thank you for working with me and, well, with you guys, I guess, to make this accessible to everyone and allow people to get into this world of blockchain development. With that said, let's get into this first video. All right, so let's go ahead and get started. In this first video, I'm going to show you how to set up a MetaMask wallet. This is actually an extension for Chrome, although it's available for iOS and Android as well. And please, even if you have an existing Ethereum wallet, because this will be storing Ethereum, follow along with these steps because you want a MetaMask wallet so you can get access to free Ethereum and use it with the different applications we're going to be using later in this series. So go to this website, click on download. I'll leave a link to it in the description, and click on Chrome and then install MetaMask for Chrome. Now, when you do this, it will install a Chrome extension. It should pin this for you, but if for some reason you don't see this in the top right-hand corner, so a little fox icon, that's the MetaMask icon, then click on this puzzle icon for extensions and just pin this. It's just going to be helpful. So click on the little pin, and then it will make it so it's persistently up in, I guess, your, I don't know, you want to call this a taskbar, bookmark bar, whatever. Otherwise, if you don't want to pin this, you can just click directly on MetaMask, and it will open up this page. Now for you, I'm sure this is going to look a little bit different because you have not yet set up an account with MetaMask. So I'm not going to walk through those steps because they're pretty intuitive, but just walk through the basic setup steps on MetaMask. You need a password, make sure that's secure. You're also going to need some secret words. You want to make sure you save those somewhere. You want to have access to them. And then once you've done that, it should prompt you to create an account. So if you don't get prompted to create an account for some reason, just click on this circular icon in the top right-hand corner and click create account. Now you can have as many accounts as you would like within MetaMask. You can see here I have two. I have account 1 and I have tutorial, and this will be very useful for us later on if we want to actually try testing out sending Ethereum between different accounts. Great, so that's kind of the basic setup. So I have account 1, notice I have 6 Ethereum. This is actually fake Ethereum. I'm going to show you how to get that in a second. And then the tutorial account where I have 0 Ethereum. All right, so at this point in time, I'm going to imagine that you've gone through those setup steps. You figured out how to get to a page that looks similar to this. And now I can show you how to get some free Ethereum. So the first thing I want to mention is that Ethereum has a few different networks. So if you click up here where it says, for you, it'll say Ethereum mainnet, but for me, it says this Gorelli test network. What you're going to do is select one of the test networks that you want to try out your application on. Now, these test networks are kind of a mirror or a clone of the Ethereum mainnet. The mainnet is the main Ethereum network. This is where real Ethereum exists, real smart contracts exist, and anything on here is real money. So you'll see this is 0.00 USD, whereas if I switch to a test network, there's no price because this is all fake Ethereum. It's not worth any money. It's just for testing, for development. So you can use any test network that you would like, and you can kind of mess around with different ones if you want. But the one that's been working really well for me recently is this Gorelli one. Now, I'm probably mispronouncing this, but this is the test network we're going to be using for right now. And I just want to note that the public address of this wallet, if that means anything to you, is available right here. So if you go copy to clipboard, let's take this and paste this, you'll see that we have this address. This is the address for my Ethereum wallet. Okay, let me go back to MetaMask here. And now we are back on the Gorelli test network in my tutorial account. Great. Now that we've done this, I'm going to show you how we can use a faucet to access free Ethereum and have it sent to this wallet. So what we can do is click on buy. And when we do this, we have directly deposit Ether or test faucet, get Ether from a faucet for the Gorelli. Now, this is the one that we want, so we're going to click on Get Ether. You can do this on any of the test networks, and it will bring you to a different website. Now, this is bringing us to some faucet. I actually haven't used this faucet. I'm going to show you how we do a different one or use a different one. But what you can do is just stick in your address right here and then request the Ether. I would need to do the I'm not a robot thing. And notice it's giving me an internal server error because sometimes these things just don't work. They are test networks, okay? So they're going to be down sometimes. There's going to be some maintenance. They're not 100% reliable, but that's fine because we're just using them to test. So you kind of just have to experiment and mess around with them and find one that's working on a specific day. Kind of annoying, but considering we get free Ethereum and we can test it out without having to pay, I am not complaining. Okay, so what I'm going to do is go back to MetaMask here. And actually, let's just copy this public address, although I already have that copied. And now we're going to go to this website right here. I'll leave a link to this in the description. Now, this website is what's known as a social faucet. Now, a social faucet means that you need to post something on social media that contains your wallet address and then put the link to that post, and it will then send you Ethereum. Now, you don't need to post on some large account or something. You can just make a brand new account on Twitter or Facebook. I think those are the two available ones right here. And in fact, that's exactly what I did. So what I did is I went to Twitter. I have this actually really old Twitter account from when I was like 12 or something. Oh yeah, July 2013. Anyways, I don't use this account, so I just signed in, and then I posted this tweet requesting faucet funds into and then this address. Now, you actually don't need to write anything other than the address of your wallet. So what you'll do is go tweet, or if you're on Facebook, you would post something, and then I'm just going to make a tweet that contains my wallet address. Going to click tweet. Then I'm going to go here, and I'm going to go share. So I'm going to copy the link to the tweet. I'm going to go here, paste that link in, and then click Give Me Ether. Now, we have a few options. Select whatever one you want. I'm just going to go with 6 ethers every day. I got to select the chimney, so let's see if I can pass this. Okay, that looks good. And it said, oh, I have a certain amount of time left until my next allowance. Okay, looks like it's because I got Ether recently from the same account. And so that means that I have to wait. But for you guys, this should work. You shouldn't have a timeout problem. I already have 6 Ethereum, so I'll deal with using that as I need to as we go through the tutorial. Regardless, this should work. It should just give you Ethereum. And then if you go to MetaMask, you should see in your account. So let me swap my account here to account 1 that you have some amount of Ethereum. All right, so at this point in time, I'm going to assume you've successfully got some Ethereum. If the test network I used didn't work, just try another one. Go through all of them. Eventually, one should probably work for you. Now, it doesn't really matter which test network you used, but just keep track of which one it was, because you will need to change some very minor steps as we go through the rest of the tutorial if you did use a different test network. But everything will still work. The general concepts are the same. You just need to alter like 1 or 2 things. Very, very small. Anyways, what I want to do now is show you how to send Ethereum, which is really easy to do with MetaMask, and how you can explore the blockchain and look at the addresses of wallets, look at different transactions that have occurred, and just show you this website here known as Etherscan. Now, Etherscan is what I like to call a blockchain explorer. You'll notice here I'm on gorelli.etherscan.io. So this is specific to the test network that I'm using. If you did use a different test network, then you're going to want to search up Etherscan plus the name of that test network and just go to that Etherscan. Obviously, this one is for the test network that I used. So what I want to do is show you that we can actually view everything on the blockchain completely transparently. It's one of the great things about the blockchain. You can just go and look at any wallet address. You don't necessarily know who owns that wallet address, but you can see every single transaction that's occurred. You can see who sent the money, how much money is in every single account. That's one of the great features of the blockchain. Everything is completely transparent. So I want to show you how we look up our own account on Etherscan. So I'm going to go here to MetaMask, and I'm just going to click on my account address right here and copy it to the clipboard. Now that I have that, I'm just going to paste it in this search bar right here and just click search. Okay, so here we go. We can now see my wallet address showing up on Etherscan. Now, if you guys go and paste this address in, I don't assume you're going to type all of it out, but let's say you did that into Etherscan, you would see the exact same page that I'm seeing, and you could view all of the transactions in my wallet. So anyways, here we are. This is my wallet. You can see I have 6 Ethereum inside of here, and I had one transaction that occurred 8 days and 3 hours ago. This is correct. That's actually when I had the Ethereum sent in, when I was kind of preparing for this video. And you can see it was on this block. I had this transaction hash, and then I have the from address and the to address. So the to address is my wallet address right here. But if I want to see where this Ethereum came from, which was the faucet, I can click on this. So when I click here, notice this has an absurd amount of Ethereum, 515,000 Ethereum, right? That's quite a bit. And you can go and look at all of the different transactions that it's sent and how frequently it's sending them. So you can see how many people are requesting Ethereum from this faucet. Anyways, let's go back. And let's actually click on this transaction hash. That's what TXN hash is. So let's do that, and let's just look at some details that we have here. Now notice it's telling us this is only from this test network, okay? Gives us the hash of the transaction, which we'll discuss later on. We have the status. This was successful. You could have a status of pending, meaning it's not yet been sent through. Then we have the block that this was attached to, we can actually click directly into the block and view everything that was associated with this block as well. We can see the miner that mined it too, which is interesting. Then we can go and look at the from address, the to address, the value of the Ethereum, the transaction fee, the gas price, and a bunch of other stuff. Now, this is really not going to mean anything to you right now, but I just wanted to show you that you can do this. You can look at all of the details of the blockchain completely for free, transparently, and anyone can do this. There's not one person who has access. You can't hide your transactions from one person. Everything is completely publicly available. All right, so now that we've looked at that, I'm just going to quickly show you how you could send Ethereum. Now, you only can send Ethereum between the same test networks, so I can't send this Ethereum to a different test network or to the main Ethereum network. Obviously, that's not going to work. But what I'm going to do here is just look at my other account. So you'll notice that if I go here, I have my tutorial account, and then I have my account 1. So let's say I want to send, I don't know, 1 Ethereum to this tutorial account. Well, I'm just going to copy the address here. Notice I'm on this test network. I'm going to go back to account 1. I'm just going to click on send in MetaMask. I'm going to paste in this public address. I'll go with 1 Ethereum. I will click next, and I can confirm this. It's going to tell me how much this will cost. I have to pay a very small gas fee. I will click confirm, and now it is sending the transaction. You can see it says pending. If I click on it here, it gives me the details, and this is very similar to what I had on Etherscan. Now, let's see if we can find the hash of this transaction. Copy address, no. Let's go copy transaction ID. Okay, so I'm going to copy that. Let's go to Etherscan here and paste this in, and let's see if we can view the transaction. And there we go, we can view it. And notice if we go to the from address, this is my address that now has less Ethereum in it than it did before because I am attempting to send money. Now, it is not showing me the pending transaction because the transaction is currently pending. It is not finished, but you get the point. This is all working, and well, we can view all of the transaction details. All right, so I just took a quick cut, and you can see that the transaction has now actually gone through. So I have a status success. The page actually updated live when I was on it, so that's how I knew this. And if I go back to the from address, you can see this transaction is now here. And sorry, it's right here actually because it's more recent, and it's saying we sent 1 Ethereum out from this address to the other address. And if we go here, we can see we have 1 Ether. And then of course, if we go back to MetaMask, and let's go to this other account. So let's go to account number 1 or tutorial. We have 1 Ethereum. So anyways, with this transaction now being completed, I'm actually going to end the video here. I just wanted to give you a brief introduction to how we actually set up Ethereum accounts, how we can send money between different accounts, the test networks and the faucets, and then of course Etherscan, so how you can actually view different transactions, view wallets, and see what's going on the blockchain. A lot of this will start to make more sense in the next video, where I actually go through a deep explanation of how blockchain technology works, how the network is secure, how transactions are sent, etc., etc. Anyways, I am going to wrap up the video here. I hope you guys enjoyed. One last massive thank you to Cartesi for sponsoring this video and helping with the content. We'll hear more from them in future videos. I hope you guys are sticking around. Make sure you subscribe to the channel, and I will see you in the next one. Hello everybody, and welcome to part 2 of this video series. In this part, I'm going to be explaining to you the theory behind blockchain technology, so specifically going through some key terms like private keys, public keys, cryptographic hash functions, what those are, how those work. I will talk about transactions, how a transaction is created and signed and secured. I will talk to you about blocks, how blocks are connected together. I will then start talking about proof of work, which involves miners and securing the blockchain. And while all of this is very, very interesting, and I try my best to break it down as simply as possible for you in this video. So in a second, we're going to hop over to the drawing tablet. I'm just going to start doing some diagramming and explaining, and I encourage you to sit back, relax, and enjoy the explanation. However, before we do that, I quickly need to thank the sponsor of this video and this series, which is Cartesi. Now, Cartesi is a company that is dedicated to making the blockchain more accessible and affordable. And when I say affordable, the reason that's important is because, as you're going to see as we go through the rest of these videos here, deploying smart contracts is very, very expensive. Now, Cartesi offers a bunch of solutions that can actually cut this cost by a factor of almost 100 and really just make it much easier to work on the blockchain. Anyways, we'll hear more from them later on, and we'll actually start using some Cartesi technology, hopefully in a future series. But regardless, they are an awesome company. They've been helping me come up with the content for this video, and I'm just super grateful and happy to be working with them. Regardless, let's dive into the video. Alright, so I'm now on the blackboard. Ignore the black screen. There will be some drawing in 1 second. But for now, I'm going to start by explaining to you some key terminology related to cryptocurrency, specifically private key, public key, and address. So let's actually start by looking at what's known as a cryptographic hash function, because it's very important to understand this concept. So we have a function, let's say f of x, and this is equal to y. This means you take some input x, you get some output y, pretty standard. Now, with most regular functions, you can compute what's known as the inverse. Now, the inverse of f is known as f inverse, and then you would take y, and this would give you x. So the idea here is that given some output, and given the function that computed that output, tell me what the input to that function would need to be to get that output. So the inverse is like this. You take the output, you pass that to the inverse function, and it gives you the input required to pass to the original function to get that output. So let's just look at one concrete example. Let's say we have something like y is equal to x plus 2. Well, if 2 is my input, then y is 4. Now compute the inverse of this function. The inverse of this function you simply compute by isolating x. So you would just say y minus 2 is equal to x. That's the inverse. And so if I give you the value 4, you can tell me 2 was used to compute that. Great, so now that we understand what the inverse is, the first property of a cryptographic hash function is that it has no inverse. So we're going to call this now the hash function. So let's do hash func. This is going to be our input, and this is going to be our hash, otherwise known as a digest, okay? You don't really need to know that, but hash is what I'm probably going to be referring to this as we go through this video. So the first factor, or the first property of a cryptographic hash function, is that it has no inverse. Now what that really means is that given y, you cannot find x. So if you're given the function and the output of the function, there's no way to figure out what the input is. That's very, very important. So to clarify here, when I say we can't find the inverse of a cryptographic hash, that's not necessarily true. Now it's important to note that here I'm not talking about the cryptographic hash function, I'm talking about the actual hash itself that was the output of this function. So currently, there's no efficient way or formula that we know that we can use to take an individual hash and determine its inverse. However, it may be possible to invert a hash using a brute force approach where you would blindly guess and try several different values until you determine what the original input value was that generated this hash. Now, this brute force approach would take billions of years to perform, and that's why we say a cryptographic hash has no inverse, because it would take an extremely long and unfeasible amount of time to compute it. So yes, theoretically, it may be possible to compute the inverse of an individual hash, but it would take such a long time that we just simplify things by saying it has no inverse. So moving on, the next property of a cryptographic hash function is that it is deterministic. That means that any input x1 always leads to one output y1. So second property, deterministic, again meaning that one input always points to the exact same output. Next property is that every output is unique. So if I pass x1, I get y1. Nothing else points to y1. So if I have x2, it's not possible for me to get the same y1. As soon as I have something like x2 and they both point to the same output, this is no longer a cryptographic hash function. So again, I need to add a small clarification here. Theoretically, it is possible to have two inputs mapped to the same output using a hash function. Now, when that happens, this is known as a collision. Now, the thing with cryptographic hash functions is that for that to happen, for you to find a collision, just like finding the inverse, that would take you, say, billions of years, a very, very long time to do. So we can kind of operate on the assumption that there will be no collisions, but theoretically, if we're talking about the exact definition, there could be. So I'm going to kind of be speaking in this video in definitives. Just understand there is some nuance behind those, but it's just much easier to operate under these assumptions. And well, hopefully that makes sense. Okay, so those are the first three properties of this function. The next is that the hash that you get is uncorrelated to the input. So what this means is that if I have something like f of 1, 1, maybe this gives me a hash of a, b, c, 2, 3. Now, you might be trying to guess here that if I had a hash of 1, 2, that it would give me something similar to this. Maybe you would think we get A, B, C, 2, 4, or something along those lines, because you would imagine that the output here is correlated to the input. But with a cryptographic hash function, this is not the case. If I were to pass 1, 2, so just one number is different, I get a completely different hash. So I might get something like DFA294 or 7 or whatever. You know what I mean? We just get a completely different hash. There's no way to reasonably guess what the hash is going to be by looking at the input. All right, so that is great. The very last property is that this is quick to compute. So computing the hash of some input is very, very fast. Those are the 5 properties of a cryptographic hash function. Okay, so moving forward, we're now going to talk about private keys, public keys, and addresses. So let's start with our private key. Now, the private key, I like to think of as the master password for our Ethereum account. So the private key is actually what allows us to access our account and to send money. So if you have access to a private key, you have access to an Ethereum account, and well, you can send money on that account. That means you need to keep this private. You do not want to share this with anyone. And in fact, we don't even look at what our private key is. When we use MetaMask, it's generated for us and stored in an encrypted fashion in kind of the back end of MetaMask so that no one can actually see it. Now, when I say encrypted, this is actually one of the reasons why we need to pass a password when we created our MetaMask account. So what happens in MetaMask is it will generate a private key for us, but it won't store it in plain text. So if the private key was 123, it will never store 123. Instead, it will store what's known as an encryption or an encrypted version of this private key, and it will encrypt it using our password. So we have some special function that's going to take in our private key and our password, and then it will give us some output, okay? And then the only way to go from this output back to what this private key is to know what the password is, okay? So we need to use the password every time we sign in so that we can decrypt our private key so that we can then use the private key to actually send transactions. Okay, that is the private key. And what the private key actually is just a string of characters. That's really all it is. It's extremely long. And again, you usually are not going to be looking at this yourself. It's going to be stored in some secure way. So next, from our private key, we generate what's known as a public key. Now, the public key is generated from the private key. So you need the private key to get to the public key, and we use a cryptographic hash function to generate this, which means if you know the public key, there is no way to go back to the private key. You cannot do that because the way we generated it was using a cryptographic hash function. That's very important because someone could theoretically figure out your public key. If they do figure out what that is, that doesn't matter. There's no way for them to go to the private key. Hence why this is private and this is public. The public one can be shared anywhere. Okay, moving forward, the next thing we have is our address. Now, the address is generated from the public key. So a private key and a public key actually make up an Ethereum account, and then the address is what you're going to actually send money to. Now, what the address is actually a few characters. When I say a few, it's something like 20 characters of the hash of this public key. That's pretty much all I will say. It's kind of just a simplified version of the public key, and the way you get the address is you generate it from the public key. So you go private key, address, and from the public key, again, you cannot get back to the private key. From the address, you cannot get back to the private key, and that's very important because as soon as you have the private key, you have access to the Ethereum account. So you give the address to whoever you want to send money to you, and that is how you will reference your account on the Ethereum network by this address. Great. So the whole point of the address, as I was saying, is it's just a simplified version of the public key. So it's a little bit easier to be using on the blockchain rather than writing the public key everywhere. So now that we understand private key, public key, and address, we need to talk about transactions and then how the blockchain actually handles transactions. So let's say we have the example where we have maybe account 1 and account 2, and account 1 wants to send some Ethereum, maybe 0.1 ETH, to account 2. How do we do this? Well, to do this, we need a transaction. Now, anyone can create transactions on the blockchain. Anyone can do it. And what's involved in a transaction is an amount. So this is going to be 0.1 ETH. We're going to have a to wallet. So what address we're going to. So we're going to be going to account 2. And then from, this is going to be account 1. Now, the only problem right now with this transaction is that we kind of have to trust that who's making this transaction is the person who's sending the money, right? The from address. But theoretically, account 2 could make this transaction and say, oh yeah, account 1 is sending me all of its Ethereum. Anyone could just make a transaction and you could add as many as you want and you could just throw them on the blockchain. And well, if there was no security, then you would just have random people adding transactions all of the time. That is why we have something known as a digital signature. So a digital signature is a very special hash that involves the actual private key of the account trying to send the money, so of the from account, as well as all the information associated with the transaction. Now, I won't talk too much about the signature because it's pretty mathematically complicated, but to be able to actually create a transaction that is valid, what you need is the private key of the account you're trying to send Ethereum from. So this signature here, again, as I was saying, is going to require the private key, as well as the transaction itself. So the transaction I'm just going to represent by TX. And then there's actually another part of this as well. And anyways, you hash all of this. It gives you some, random string of characters. And this string of characters you can verify is a correct signature for this transaction. Now, the way that you actually verify this signature is simply by using the public key of the account that's sending this Ethereum. So if we see a transaction that's coming from account number 1, we don't need to know account number 1's private key to determine that the signature is valid. We can just use their public key and a special kind of mathematical computation to determine that this signature is valid and that it was actually signed by the account that's sending the Ethereum. Because again, you can only send this Ethereum if you have access to the private key of the account that's supposed to be sending the Ethereum. So just know for now that you can verify a signature very easily without knowing the private key of the account. You just use a certain aspect of the public key. I'm not going to go into too much more detail, but that is how you verify a signature. So anyways, that is how you actually secure a transaction. You digitally sign it using your private key and a few other things. We don't have to manually do that ourselves. It's done by MetaMask when we actually send a transaction. Okay, so let's remove all of this. And now let's see how we actually associate a transaction with a block and how we actually, use the blockchain and put a transaction on the blockchain. Because right now we made this transaction, that's fine, but we need to send it on the blockchain. We need to attach it to a block before it's actually going to go through, before our money gets sent to the other person. So let's look at what a blockchain is. Let's say we have one block like this, another block like this, and a third block like this. Now, all of these blocks are connected together in a chain. Now, they would be of equal size. I've obviously drawn mine a little wonky here, but all of these blocks contain some information on them, as well as all of the transactions and smart contracts that were added to them at the current point in time. So what this blockchain actually does is it represents a digital ledger of the entire history of the Ethereum network when we're talking about Ethereum here, right? So every single transaction is a transaction that has taken place, and we know the order in which they took place because they're ordered on the block, and then all of these blocks are ordered. And this is very similar to something like a ledger that you would have at a bank. So a bank would keep track of every single transaction you had sent and everyone else had sent. It would know all of that information. Well, same thing here with the blockchain. We just do it in a different way. Now, one of the key properties of the blockchain is that it is decentralized. This means it is not controlled by a bank, is not controlled by a single person. It is controlled by a network of computers that are owned privately by random people around the internet. And the reason why this is important is because as soon as something is owned centrally, so by one person or one organization or one entity, they have the ability and the power to do something with it that is corrupt or that is malicious or that anyone else just doesn't have the ability to do, or that they shouldn't maybe have the ability to do. For example, if you own a bank account, the likelihood this is going to happen is very slim, but theoretically, the government could just force the bank to hand over all of your funds. Maybe you need to pay your taxes or something, whatever. The idea is there's a central organization that controls this, and so at any point in time, this central authority could go in and actually modify what's on the ledger. They could change the account balance. They could take money from you. But here, when we're talking about a blockchain, that is actually not possible because this is not owned by one person or one entity. It is used and controlled by all of the computers around the world that contribute to the network. And we'll talk about what those are in a second. But to be able to do anything malicious on the blockchain, you would have to control almost all of the computers around the world that are storing a copy of the blockchain and that are on the blockchain network. Okay, hopefully this makes a tiny bit of sense, but let's have a look at one individual block, kind of see how that works in the context of transactions, and then we'll talk about proof of work and a bunch of other very important aspects of the security of the blockchain. So let's say we have a single block, okay? We can just call this something like block number 2, okay? Now, the reason why I'm naming it number 2 and not number 1 is because the first block in a blockchain is a special block, contains some configuration and initialization related stuff because, well, it's the very first block. So that's kind of a special one. We're going to ignore block 1 for now and just move straight to block 2. Now, block 2 is going to contain some transactions on it. The transactions I'm going to represent by these squiggly lines. Now, these transactions are exactly what I showed you before. They have a to address, a from address, an amount, a signature, and they have a few other things as well. In fact, every time you send a transaction, you usually have to pay a very small fee, and this fee will be given to the miners that are trying to secure and validate a block. Anyways, this block has some transactions on it. Now, this is where we get into the concept of miners. So miners are computers that are sitting around the world that are supporting the Ethereum network. They're actually what allow it to run, and they're what secure the blocks and make sure that you can't just hack the network, okay? So we'll dive into miners in a second. I just want to take a quick step back here. So whenever you're sending a transaction, you need this transaction to be associated with a block, and this block has to be mined, which we'll discuss in a minute, before your transaction actually goes through and is completely successful. Up until that point, your transaction will be pending, but once it's been added to a block and that block has been mined, then it is successful. Now, a new block is added to the Ethereum network approximately every 15 seconds, so very, very quickly. Anyways, now let's talk about mining. So, what are miners? Well, as I discussed, miners are just computers that are sitting around the world. This is going to be my computer, just a bunch of kind of deformed squares here, right? So there's a bunch of these guys sitting all around the world connected to the Ethereum blockchain. Now, every single time a new block is created and all of the transactions are added, it gets sent to every single miner. So all these miners are kind of nodes on the network. They're all sitting there waiting for transactions to get added to the current block. When this happens, what these miners do is try to mine the block. Now, mining the block consists of performing some computations, particularly some very difficult computations that are very time-consuming, and trying to guess a number that makes the hash of a block, which we're going to get to in a minute, have some specific properties. Now, the point of doing this for these miners is that if they are able to guess a specific number, they successfully mine the block and they will be given a reward. So let's say miner 1 actually guesses what the number is. I'll discuss what that number is in a second, and they will be given some reward. Now, this reward will be made up of two things. The first thing it will be made up of is a block reward. Now, a block reward is a reward that is hard-coded into the Ethereum network and actually decreases over time, and this is new Ethereum that will be created and given to the miner as a reward for mining this block. I'm not sure what the current block reward is right now. It's probably something like 1 Ethereum, but the point is that this is new Ethereum that then gets added to the ecosystem and is circulating around. So yes, some cryptocurrencies, and here specifically Ethereum, do have an inflationary aspect to them because new currency is being created, but it's not something you really need to be worried about. And while there's a whole field of cryptocurrency called tokenomics that kind of discusses this and why this is maybe actually a good thing, I'm not really going to get into this in this video. Point being, don't be too worried about the fact that new Ethereum is being created. So the second thing that you're going to have is going to be your fees. Now, every time you send a transaction, you're going to pay a very small fee. This fee goes to the miners that are mining the block. And so the successful miner, the miner that actually guesses the number that mines the block, is going to get the block reward and any fees associated with all of the transactions on the block. Okay, hopefully that makes sense. I'm just trying to explain the incentive structure here for people to actually mine. So continuing, now we need to talk about what the miners are actually doing. What the miners are doing are trying to guess a number that gets added at the end of the block. So I'm going to say num equals question mark that makes the hash of this block equal to a certain number. So what they're trying to do here is they are trying to find some number that they can add as kind of a dummy transaction at the very end of the block, so that when I take a hash of this entire block, so I run this through a cryptographic hash function, the hash that I get starts with a certain number of zeros. I believe right now what they're trying to find is a number that starts with 30 zeros, but it could be actually higher or lower. I'm not sure what the exact number is. The point is that what these miners are going to be doing is trying to guess some number, right? This is a random number that you add at the end of the block. And then when you hash the entire block, so all of the transactions associated with the block and the number together, it gives you some hash, some digest, right, that has 30 numbers at the beginning, or 30 zeros at the beginning, sorry. And then the rest of it doesn't really matter what that is, but you're just trying to find something that has a certain number of leading zeros. So the point of this is that the more zeros that you have in that number you're trying to guess, the harder it is to guess that number, because the probability just decreases that you're going to guess the correct number right here. And again, I'm just really trying to reiterate here that what's going to happen is you're going to take a hash of all of this, everything inside of the block, including this number. And then you want it to give you some number that starts with 30 zeros. But the thing is, there's no way to figure out what this number is other than just guessing and checking, because the cryptographic hash function has that property that there's no known inverse. So since we can't compute the inverse, we have no better way of finding out what this number is other than guessing and checking. And so these miners are just guessing and checking as quickly as they possibly can, and the one that gets the correct number then adds that to the block, that mines the block, and then we create a new block and continue moving forward. Now, this is an oversimplification, but that's the general idea of what these miners are doing. Okay, so hopefully that kind of makes sense, but that is what these miners are attempting to do. And you might be wondering, well, there's so many miners, so is it only actually one miner that's guessing this number? And the answer is yes. At every single block, you're only having one miner that is going to guess what the correct number is and get the reward. That's why you'll have pool mining, which means you'll have like hundreds of thousands of computers that will split their processing power. They'll say, okay, we're all going to try to guess a number together. And if any of us get the number, we're going to split the rewards between everyone, because the probability that one of us can guess the number consistently is very, very low. In fact, if you only had one computer mining and it was not mining very quickly, your probability of ever getting a block reward would be almost zero, because there are just so many other computers doing it, and you would have to get extremely, extremely lucky. So that's why you would mine with a bunch of other people, so that your probability of getting a reward is much higher, and then you would split that based on how much work all of you have done. Okay, so let's continue here. Now what I want to do is draw a few blocks, and we'll see how these are connected and kind of the security aspect of this. So let's just paste this block over here, and for now we can just go with 2 blocks. Okay, so we have block 2, and then this guy is going to have to be block 3. Let's fix your corner right there. Okay, so we have block 2, and we have block 3. Now this would be coming from block 1. We don't need to worry about that right now. Now the thing is, these blocks are connected together, right? So we have block 3, we have block 2. Block 3 is connected to block 2, and obviously it comes after block 2. Now, how do we know that? Well, obviously these arrows aren't actually there. We don't really have arrows connecting these things, but what we do have is a field in every single block that represents the hash of the last block. So we have something like last is equal to, and then whatever the hash of this block is, including the number that we guessed, that is what we put right here to represent this is the last block in the chain. So let's say when we hash all of this, we get a number that is 000049AB. Now this will usually be a hexadecimal number that is 64 characters long, but for simplicity, we'll just go with this for now. So to get this hash, we would also have guessed this number, let's just say it's 7, and what we were trying to do was to get a hash that started with 4 zeros, which we've done. So next, what we'll do is we'll write this hash here, so 000049AB. So now in block 3, we know the previous block was block 2, and block 2 would also have this field that would say last is equal to the hash of whatever block 1 is. So now block 3, we get a bunch of transactions on here, we add them all on, and we say, okay, we want to mine block 3. So what we need to do now when we mine block 3 is we have to find some number such that when we hash all of this, including this last field, right, that's going to be included in the block what we're hashing, we get a number that starts with 4 zeros. So what this really means here is that if the hash of block 2 ever changes for some reason, then this is no longer going to be correct, because this is going to be referencing block 2, which now no longer exists, and so this will be disconnected from the blockchain. You can kind of imagine that this arrow would get erased. Now I'll continue explaining this, but again, what we're doing is we're trying to mine block 3. So we'll guess some number. Let's say we guess some number 9, and then we end up getting some hash here. I guess I can just do it in maybe a purple color, 000, and then maybe this is 79BA, okay? This is the hash that we end up getting. So now where the real security feature of the blockchain comes in is that let's say I am a malicious entity here, and I want to change one of the transactions on the blockchain. So let's say I take my copy of the blockchain, and I go to block 2, and I change the transaction. Instead, I add this fraudulent transaction right here. Well, as soon as I change this transaction, this hash here changes, right? And the reason this is going to change is because when I take the hash of this block, now since this transaction has changed, I get something completely different. And so what I'm probably going to end up getting here is something that doesn't start with 4 zeros. So say maybe I get 102ABBC1. That's my hash. So now since this hash doesn't start with 4 zeros, I need to recompute this number and remine this entire block, because now the number 7 is no longer correct to give me a hash that starts with 4 zeros. So let's say I'm successful in doing that, and I guess, the number, let's go 275 or something. And now I get a hash like 0001234. Okay, that's my new hash. Well, now the problem is this hash does not match this hash right here. And so this block is disconnected from this block. And so if I want to actually keep this fraudulent transaction in block 2, what I need to do now is modify block 3, because I have to change this last to match what my new last on block 2 is. So what I do now is I come here, and I would need to change this now to whatever this is. So 0, 0, 0, 0, 1, 2, 3, 4. But now that I've changed this, the hash here is going to be completely different, right? Because we're going to get a different value when we have something different inside of the block. So now I get a hash maybe that doesn't start with zeros, right? 1, 0, 0, 2, 3, A, B, C, whatever, some random hash. So now I need to recompute this block, recompute this random number, and remine it so that I now find a hash that starts with 4 zeros. And you get the point. I have to do that for every single block in the blockchain, right? Because these blocks are connected together. And as soon as these blocks are no longer connected, I don't have a valid blockchain. And if I try to send this on the Ethereum network, all of the other computers on the network are going to be like, no, that is not correct. Your blocks are not connected. Your hashes are all messed up. And I have a different version than you have. So no, I'm not going to accept that as a transaction. I'm not going to accept that as a block because that is fraudulent. So hopefully this makes a bit of sense, but this is a concept known of hashes of hashes or hashing of hashes. And so what we're doing is we're taking a hash of this block, putting it inside of here, and then taking a hash of this block that contains the hash of the previous block. And so any change to the previous block means that this will no longer be valid. And so we have to change pretty well every single block in the blockchain to be able to modify everything. And that is why this is so secure. And that is what leads me to the concept of proof of work. So what we're doing when we're mining is we are proving that we have spent a certain amount of time before adding this block to the blockchain. And the reason that's important is because the more time we spend, the harder it is to modify the blockchain. If you had an absolute supercomputer and you could just remine these blocks instantly, then you would be able to go and change the blockchain. That would be fine. You could do that because you could just regenerate every single block with all of your fraudulent transactions added. However, since that's pretty well impossible, and we have so many computers working on the blockchain at the exact same time, for you to be able to do that, you would need more computing power than all of the other computers on the blockchain combined, and you would need to be able to not only rewrite the entire blockchain previously to what it's currently at, you would also need to be able to catch up to all of the other computers that are working on the new blocks being added to the chain and kind of beat them. You'd be like racing against them in a sense. I'm sure this is very abstract, but this is what makes the blockchain so secure. That these blocks are actually linked together. You need to perform this mining process, which is proving you've done a certain amount of work. This work takes some amount of time. This amount of time you can calculate using probability, the probability you're going to guess a random number and how quickly you can guess random numbers and all of that. And as the blockchain continues to grow, being able to potentially modify it becomes harder and harder and harder. So anything that is added to the blockchain is pretty well permanent, and you cannot remove it without having to rewrite the entire blockchain. So this is all great, but one other thing I will mention here is that another security feature that's built in is that every single computer that is mining the blockchain or mining the current block has a copy of the existing blockchain. And so what that means is that if you try to change something on, say, the current block, every single other computer knows what the current block looks like. And so if you're submitting a block that looks different from that, it's going to be able to tell that very, very quickly. It can just take the hash of the block. If it doesn't match the hash that it has, it's going to be like, no, this is the incorrect block. I'm not going to accept this block or accept this transaction because, well, it doesn't match what I currently have. So hopefully this is all starting to come full circle just a little bit. You don't have to understand this stuff super, super well, but you just have to have a general idea of why the blockchain is so secure, this concept of decentralization, and kind of how transactions get added to the blockchain and what mining actually means, right? And that's the reason why there's been a huge GPU crisis in the past and recently as well. A bunch of people are mining cryptocurrency for the incentive of trying to earn these different rewards. All right, so that is all great. And really what I just spent the last 10 or 15 minutes explaining is proof of work. So pretty much everything starting from when I started talking about blocks was trying to explain to you how proof of work works. And while that uses raw computing power, typically GPUs, to perform hashing, which then secures the blockchain in the ways that I mentioned. However, and I understand some of you may be a little frustrated here, Ethereum is actually switching over now to proof of stake. I'm not sure exactly when that's going to happen, but it's supposed to have happened for a long time, and I know it's going to happen very, very soon. And the difference is that with proof of stake, which is going to be kind of the new method and algorithm, this is a type of consensus mechanism, which is going to be used to validate the transactions versus using raw computing power. Now, proof of stake pretty much means that if you own cryptocurrency, you can stake your coins. By staking them, you're kind of putting them in a locked container. That's the way you can think of it. And what this does is give you the right as the staker of these coins to check new blocks of transactions and to add those to the blockchain. Now, I'm not going to explain proof of stake in this video. Maybe we'll explain that in another video. Point being, Ethereum is slowly switching over, or actually probably pretty quickly switching over to proof of stake, and that's going to be the new method. Now, I will just say that even though Ethereum is switching over to proof of stake, that does not mean that what I just explained to you was a waste of your time. It is still very, very valuable to understand how proof of work works, and that is currently what is being used and is being used for a lot of other cryptocurrencies as well. Proof of stake is just another method of doing this, and while I'm not going to explain that further in this video, but maybe we'll talk about that in the future. Regardless, with that said, that pretty much wraps up everything that I needed to cover. If you guys made it to the end of the video, give yourself a pat on the back. I hope that this maybe cleared up how the blockchain works and gave you at least a little bit of the insight into the theory behind it. If I were to go through and explain all of the mathematics of this, not only would I probably make a ton of mistakes, but this video would probably be 4 or 5 hours long. So really, if you can grasp the core concepts here, you have a good enough understanding to kind of proceed and to move forward and start writing smart contracts. And to be quite honest with you, you don't necessarily need to have all of this mastered to actually write a smart contract. It's just very helpful and something that I think is fundamental before moving forward. Anyways, with that said, I will finally end the video here. Thank you guys again for watching. If you enjoyed, leave a like, subscribe to the channel, and I will see you in another one. Hello everybody, and welcome to the third video in this Blockchain for Beginners tutorial series. In this video, I'm going to be giving you an introduction to Solidity and showing you how to write and deploy your first smart contract. This is really, really cool. I had a lot of fun messing with this before the video, and I think you guys are going to be amazed at how simple it is to actually write a smart contract. Anyways, I should mention that Solidity is the programming language typically used for deploying smart contracts and writing Ethereum smart contracts, and so that's why we're going to be using it. Now, in terms of kind of some prerequisites for this video, I'm going to assume that you have some understanding of programming, some experience writing in maybe a different programming language, just because in this video, I'm not going to explain the very basics like things like variables, functions, and all that stuff that's kind of common knowledge when it comes to programming. Of course, I'll go through the Solidity syntax, and we're really going to learn by actually just doing a bunch of examples and not focusing a ton on theory. Last thing I will say is that you do need to have your MetaMask set up if you want to deploy this to a test network, so an Ethereum test network. If you don't have MetaMask set up, that's fine. You just won't be able to follow along with that step in the video. All right, so with that said, we're just about ready to get started. I just want to quickly thank Cartesi again for sponsoring this video and this series. They're an awesome company, again, dedicated to making the blockchain more accessible and easy to use. They've really helped me a ton in terms of coming up with the content for these videos. Well, I hope you guys appreciate that. In the future videos in this series, we're going to be talking about how we can actually use Cartesi to fix some of the scalability issues with smart contracts, because you're going to start to see some of the problems that can actually occur when we write a smart contract, because they're a lot different than your traditional code. Anyways, let's go ahead and get into the code. All right, so I'm here on my computer, and the first thing I'm going to discuss is just setting up our environment for writing code in Solidity and deploying smart contracts. Now, of course, you can write contracts in VS Code or any local code editor, but instead for this series, I'm going to use an online IDE called Remix. Now, this is a browser-based IDE. It's completely free, and it's super beginner friendly and allows you to actually deploy and test your smart contracts directly from the browser. So I'd recommend that you use this. You can check it out from the link in the description, or just Google Remix IDE. Again, completely free, and once you click on that link, it should bring you to a page that looks like this. So for now, what I'm going to do is just give a quick tour of Remix. Then we'll talk about smart contracts, what they actually are, how they work. Then we'll start writing some code and going through some examples of smart contracts. So the first thing we want to do here when we open up Remix is we just want to install a few extensions specifically for Solidity. So you can write other stuff in Remix, not just Solidity code. So that's why we want these extensions. So what we're going to do is just on the left-hand side here, go to this plugin manager. It looks like a plug. And what we're going to do is search for Solidity. Now for me, I already have these extensions installed, but what you're going to want to install is the Solidity compiler, the Solidity static analysis, and then the Solidity unit testing. Now you don't really need the unit testing, but you might as well just install it while we're here. So install those 3 plugins, and once you have them installed, we're pretty much ready to start writing Solidity code. Now you're going to see in the left-hand side here, let me zoom in a little bit, that we have a bunch of, I guess folders, directories, and inside of here we have some different smart contracts, we have some scripts, we have all of this kind of stuff. You don't need to worry about any of that. This is all just kind of test code that's provided to you. We're not going to use any of this. We don't even need to look at it. So you can kind of just ignore it for now. What I'm actually going to do to get started is I'm just going to make a new file. So I'm going to click on this little file icon right here. And then I'm just going to call this test.sol. So .sol is the extension for a Solidity file. So that's why we're going to use that. When I do that, it will open up a brand new file. Notice we have the little Solidity icon. Now we can start actually writing a smart contract. Now, one thing to notice here is there's stuff like GitHub integrations. You can create new directories. You can upload files. You can also have different workspaces. So right now I'm in a workspace I created called tutorial, but you also could make a new one by clicking this right here. I guess this is renaming a workspace. And then of course you can delete it. I'll let you look at that yourself. Pretty straightforward. Anyways, all we need to do is get to kind of a file that looks like this, just an empty Solidity file. So I'm just going to zoom in by clicking this plus icon here so you guys can actually read the code. All right, so now that we're here, we might as well write a very basic smart contract. I'll briefly show you how it works and how we can run it. Then I'll actually discuss smart contracts in detail. So how they work, how you call them, and how they're different from traditional code, because they are much, much different than anything you would have seen before. Okay, so what I'm going to do is zoom in a bit, and let's start by writing what's known as our pragma line. Now, the pragma line is required at the beginning of all of your Solidity files, and what this does is actually tell Solidity what compiler version this file needs to use. So there's a ton of different compilers that are accessible for Solidity. You just need to define the minimum compiler version. So I'm going to say pragma, Solidity, and then I'm going to say 0.8.10, and then put a semicolon like that. So for all of your lines, you're going to have semicolons at the end, very similar to something like Java. Okay, so we have our pragma line, again, just pragma, Solidity, and then the minimum compiler version. If you want to see the compiler versions, you can go to, I believe it's this tab right here, and it will show you all of the compiler versions. So notice we're on 0.8.10, so I'm just using one of the latest versions that we have. Okay, and then for language, of course, that'd be Solidity, and you're just going to have compiler default. Now here, you can actually manually compile your Solidity code. I'll talk about that in a few minutes. For now, though, let's continue writing the rest of our contract. So after we do our pragma line, the next thing we need to do is define a contract. So I'm going to say contract, and then I'm going to give this a name. Now I can give this whatever name I want. I'm just going to call it my contract. So what I've just done is created a smart contract, okay? That's all you need to do. You write the word contract, give some name. The casing you're supposed to use for this name is Pascal case, which means you're supposed to have capital letters for every single word. And then inside of here, we can start defining some variables, some functions, and methods. Sorry, not functions, methods is what I mean. Anyways, for now, I'm just going to define a very basic variable. Then I'm going to show you how we actually deploy and test this smart contract. And then we'll continue with some theory and looking at this more in depth. So for now, what I'm going to say is uint. This stands for unsigned integer. And I'm just going to say that this is public, like this. I'm going to call this x, and I'm just going to make this equal to 21. Okay, super straightforward. This is just me defining a variable. The type of the variable is an unsigned integer. It is public, meaning anyone can view it. Its name is x, and its value is 21. So now that we have this contract, what we need to do is compile the contract and then deploy it. So all of our contracts in Solidity need to be compiled into bytecode. This bytecode is then sent to the Ethereum network where the contract is deployed, and then we can call the contract. So let's just look at a quick example of doing this. So we can manually compile by pressing compile. We actually don't need to manually do this. When we deploy it, will automatically compile for us. Anyways, I've compiled the contract right here. Notice I have my compiler version, Solidity compiler default. Then what I'm going to do is go to this tab right here. So just below it, let's see what this one's called, deploy and run transactions. And here, what we can do is choose a few different options for actually deploying our contract. So if you go here, notice we have a bunch of options. We have Web3 provider, injected Web3, JavaScript VM, and then we have the Berlin version of the JavaScript VM. Now, the JavaScript VM is what I'm going to use for right now, but what this is a virtual machine that simulates the Ethereum network in your browser. So this means you don't actually have to make any real transactions. You're not actually adding this to a legitimate blockchain. You're just simulating it so that you can test this directly in your browser. Now, if you refresh your browser, what's going to happen is anything that you've been simulating in the JavaScript VM is going to disappear because, well, it was being stored in, I guess, the cache or whatever inside of your browser. Point is, JavaScript VM is kind of a testing environment, and when you're actually going to deploy this smart contract for other people to use, you need to deploy it to what's known as a Web3 provider or an injected Web3. Now, injected Web3 is actually going to use whatever network your MetaMask is on. So if I do this, what's going to happen is when I try to deploy this contract, it's going to open up MetaMask, and it's going to require that I actually do a transaction to deploy this contract. Again, we're going to look at that in a second. For now, I just want to quickly show you deploying it and running it, and then we'll get into the theory. So I'm going to go to JavaScript VM, and notice here that when I do this, it's going to give me a bunch of different accounts that have 100 Ethereum. Again, this is just testing, and the point of these different accounts is that I can actually use all of them with my smart contract. Because every time I deploy the smart contract, I want to call a function on the smart contract, I need to make a transaction to do that, and that requires an account to make the transaction with. So for now, I'll just select this first account. I could copy the address here if I wanted to do that. The gas limit, just leave this the same for now. And then you could pick an amount of Ethereum that you actually want to send with this transaction. Now, I don't want to do that for now. I don't want to send any Ethereum. All I want to do is deploy my smart contract. So I'm just going to click on deploy. And then you're going to see down here, it's going to show you my deployed contracts. So I now have a contract. Notice it's showing me this little button X. And if I click on this, it gives me the value of X. Okay. Very, very simple. That's all you need to do to deploy a smart contract. We'll talk about this more in a second. What I want to do now is hop over to my drawing tablet and start talking about some of the theory behind smart contracts and how they actually work and why we kind of need to go through this. All right, so I'm here on the drawing tablet, and I want to start by discussing how we deploy a smart contract. Then I want to talk about their use cases and go through a few properties of them. So as we saw, we had a smart contract, and we stored this inside of a .sol file. Now, this is our Solidity file, and this is what we refer to as our source code. Now, the source code is simply the code that we write as a programmer. It's the closest to English. It's the easiest for us to understand. It is the source code, okay? This is where we actually write Solidity code. However, this code cannot be executed on the Ethereum network. So what we need to do is compile this by running it through a compiler into something called bytecode. So the first step when we're deploying this contract is we run this through a compiler. This compiler is capable of taking one language and translating it into another. And what we get here is now what I'm going to refer to as the bytecode. Now, the bytecode is just a special type of code that the computer can actually understand and execute. And in almost every programming language, what's occurring is you're taking source code, you're compiling it into bytecode, and then that bytecode is being interpreted by an interpreter. The interpreter you can kind of think of as a mini computer in a sense that's actually going to be able to take all of this code, read it, understand it, and then tell the CPU of your computer how to execute it. The interpreter is typically known as a virtual machine. Anyways, you don't need to know too much about that. Point being, you take source code, compile it into something like bytecode. Bytecode is then something that the computer can actually understand and execute, and so that's how your code actually ends up running. Anyways, at this point, we now have our bytecode. So we've taken our Solidity code, we've ran it through the compiler. By the way, Remix will do this for us automatically, so you don't need to manually compile the code. And now we have our bytecode. So let me just move my bytecode over here. So now that we have this bytecode, this is the code the Ethereum network can understand and that computers can execute. But how do I actually get this now to the blockchain? Well, what I need to do is I need to create a transaction. Now, I just want to quickly mention here that what a smart contract is just code that's sitting on the blockchain. So all we're doing is we're taking this bytecode, we're putting this in a transaction, and then this transaction is kind of special in the sense that it requests to create this code, this smart contract on the Ethereum network. So what happens is we make a transaction, we throw the bytecode on this transaction, we pay some fees, and then we kind of upload this or send this in a way to the Ethereum network, okay? So just like sending money between different accounts, except in this case, we're making a transaction that is adding this bytecode as a smart contract to the Ethereum network. Now, like all other transactions, the first thing that needs to happen here is this transaction needs to be associated with a block, then it needs to be mined. Once it's mined, then it is on the Ethereum network. Now, what that means is just like any other transaction, anyone can go and see this. They can see the transaction. They can see who created the smart contract. They can see all of the code of the smart contract. They're able to view when you created it, the balance of the smart contract, all of these other things. And this also means that once we add this smart contract to the network, we can never change it. We cannot mutate it, we cannot modify it, we cannot change it or delete it. And the reason for that is the same reason that we can't delete transactions on the Ethereum network, right? Because that's the way the blockchain works. It is forever there. It is a ledger of everything that has happened. It is completely transparent and trustworthy. And that's actually the main point of our smart contracts. So hopefully that makes a bit of sense. We're going to continue to clarify this in this section. Point being is that the reason we create smart contracts is because we're taking advantage of the security features of the blockchain to make people trust the code that we are uploading. So let's take an example where we want to write some type of poker application or a casino or something that involves money, right? Something that's going to have money being transacted from either us to the client or from the client to us. Well, if someone comes to our website or we go to some casino website, for example, most times we can't see the code, right? We have no idea what's actually happening in the back end. We could easily be getting ripped off. Maybe our money's being stolen. Maybe the odds are not in our favor or less in our favor than they should be. Whatever. If we can't see the code, we don't really have any way to trust what this website is doing or how these transactions are occurring. However, if you had your code as a smart contract and you knew that the website was using the smart contract, maybe you're able to verify that in some way, then you could just go and read the smart contracts that were being used and decide if you want to interact with them or not. This means you can fully and transparently see all of the code that's actually being ran and executed. You know if you want to trust it or not, and then you can decide if you want to interact with it, right? So hopefully that makes sense. One important point there as well is that that code that you're looking at can never be changed, which means if you're interacting with the same smart contract, you know it's always going to look like that and it's always going to be trustworthy. So that's kind of the main point of smart contracts, is to allow people to trust the code, to make it fully visible to everyone, and also just to allow everyone to be able to use it, right? Although I will say it is pretty expensive to be interacting with smart contracts and uploading them to Ethereum. Okay? That is the main point of smart contracts. Now, one thing I'll mention as well is that smart contracts can have a balance. So that means you can send money to a smart contract. It can receive money. It can send money back to you. It can call other smart contracts. And in fact, we're going to start talking about that now. So let me clear the screen. And now we're going to talk about how you actually call a smart contract. So in front of me, I have a beautiful illustration. I have a contract and 2 Ethereum accounts. Now, as I said briefly, a contract can have a balance. So just like an account, a contract is going to have an address. It's going to have some type of balance. So it can actually store Ethereum, and it can send and receive Ethereum as well. So that means that the account 2 can send money directly to the contract. The contract can send money back to it. And again, account 1 and account 2, I'm just treating as regular Ethereum accounts. So ones we already would have talked about. Anyways, the contract has a balance, and that means we can go and view the balance. We can see every single call and transaction that's happened with the contract. Everything is completely transparent, just like our other regular Ethereum accounts. Great. Okay, so now that we understand that, I want to talk about the fact that a contract should really be treated like a state machine. So what I mean by that is that most contracts are going to store some type of data. So in this case, we have x equals 1. Now we need to think of this like the state of the contract. And the reason for that is that these contracts are not constantly running. They're not just always executing in the background. They need to manually be triggered from a transaction to actually do something. And so when they are not being called by a transaction, they're simply some state that's sitting on the Ethereum blockchain, okay? That's all they are. We just have the code, we have the values of the different variables, so the state of the contract, and we can access the state or request to change the state by making some type of transaction. Okay, so let's see now how we actually call a smart contract, because I keep saying this, for it to do anything, we need to call it. So calling a smart contract is really just making a transaction that requests some operation be performed on the contract, okay? So from account 2, maybe we make a transaction. So in fact, let's just write TX here representing transaction, and this transaction is going to the smart contract. Now, usually what we do is we pick some type of method or some operation we're going to be performing on the contract. So maybe we call some method here like setX, and we pass value 2. Now, the smart contract can do whatever it wants in this method, but maybe all it does is just change the state to 2. Then what we would do is we would simply change this. So now x is equal to 2. Perfect. Now, when we make this transaction, just like any other transactions, we need to sign it, we need to secure it, we're going to have a to address and a from address, and we're also going to have to pay a transaction fee, which is going to be made up of gas. Now, you can think of gas kind of like a literal gas in the real world in the sense that this contract requires gas to actually be able to execute code. So every single operation this is going to perform is going to use a tiny bit of gas, right? It's going to use a little bit of gas. And so we send what's known as a gas limit, so the maximum amount of gas that we potentially want to use in executing this contract. And then if that's enough gas, the contract will actually be able to execute. It will run through all of the code, whatever. It will have enough gas to do that. It costs us Ethereum essentially to execute code on the Ethereum blockchain. Okay, now the amount of gas you send in is required is going to depend on what the contract is doing. Some operations require a lot more gas than others. Anyways, that's pretty complicated. We don't need to talk about that for now, but just understand that what happens is we're passing along gas, and the gas allows the contract to actually execute. If it runs out of gas, just like a car, it's not able to do anything else. Okay, so that's it for calling contracts, but now let's quickly talk about contracts calling other contracts, because that is possible. So let's say I have another contract right here, and maybe this contract needs to interact with this one. Maybe it's going to call something on it, it's going to send Ethereum, whatever it's going to do. So first of all, that's fine. These contracts can interact with each other, but they can only do that if this interaction stems from, is at the root of some account sending a transaction. So these contracts, if they have no transaction, so imagine this guy's gone right here, they can't do anything. They cannot execute, they cannot call each other, they can't do anything at all. They're just sitting there idle. They are state machines. However, as soon as I have some transaction from any regular Ethereum account that goes to a contract, now this contract is capable of performing some operations, executing some code, whatever, and calling other contracts. It needs to start, though, from one of these main transactions. There's no way for this contract to call the other contract unless we start from a transaction that I've showed you right here. So all of this needs to kind of root from some transaction outside of the blockchain. So what I mean by that is from some kind of regular Ethereum account. So hopefully that makes sense. But again, you can really think about this in the sense that these contracts are idle, not doing anything unless they're called from outside of the main blockchain network, right? So from kind of a regular account. And so if no account is calling any of these contracts, they're not able to do anything. And we also need gas, which is going to be passed along with the transaction to the first contract call that we make. All right, so with that said, I think that ends the theory section of this video. I apologize if this was long, but this really did need to be covered. Now we're going to get back to the code, and I'm going to start showing you how to write more advanced smart contracts. All right, so I am back on the computer, and now what I'm going to show you how to do is how to deploy the smart contract to a real Ethereum network. So we'll go with the test network, right? Rather than the JavaScript VM, which is going to emulate the blockchain in your browser. So what I'm going to do here is change this to injected Web3. Now, when you do that, it's going to connect with MetaMask, which I assume you already have set up, and it's going to show you the test network that you have, I guess, enabled in MetaMask and the account that you're using for MetaMask. So in this case, I have my tutorial account that has a little bit less than 1 Ether. Anyways, in the same way that we deployed this when we were using the JavaScript VM, we can just click deploy. It will automatically compile this for us. We don't need to manually compile. And then it's going to actually bring up MetaMask because we need to make a transaction to do this, right? We need to create the contract. That requires a transaction. So we can look at data. This is going to have the contract data. We're going to have our details, and it's going to tell us how much it costs. Now, the bigger the contract is, the more this would cost. Anyways, this is relatively cheap. I will click confirm. Okay, now this is going to take a second, and if I bring up this kind of, terminal here, console, you're going to see it tells me that it successfully deployed the contract, okay? So you can view kind of, I guess, the output of all of the transactions and contract calls by just bringing this terminal up right here. Anyways, what we're going to see now is it shows my deployed contracts, so this is my deployed contract. Now, what I want to do is actually look at this contract, so let's see how we can do that. So what I'm going to do is go to MetaMask here. I am going to go to the contract deployment, which is right here, okay? And then you'll see that I can actually click on this button, and it will allow me to view the transaction on Etherscan. Now, I had some other transactions there. I was, of course, messing with this before the video, so you can ignore those ones. This is the one that we just created. Anyways, now we are in Etherscan, the Gorelli test network Etherscan, right? And we can see we had our transaction, it was successful, and we have the from and the to. Now, what I want to look at is the actual contract address. So I'm going to click on that right there. Now it's going to bring me to the contract address on Etherscan. So I can see the balance, I can see the content creator. So this was me, right? I created this contract at this transaction. And then it tells you that the content or the contract, was created. Now we can look at the contract itself. So we can actually view the bytecode. We can decompile that into the source code if we want. And then we have events. I'm not going to talk about that right now. That will be in the next video. Anyways, we can close that. I just wanted to, let's go back. I just wanted to show you what that looks like. Okay, so let's go back to Remix. All right, so now that we have this deployed, we can use the contract, right? So I can access the variable X. That's fine. It's going to give me the value 21. So one thing to note here is that when you're viewing the state of a contract, so we're just looking at the value of X here, right? Viewing the state, this is free. We don't need to do a transaction. It's fine. We can query the state. That's a free operation. And the reason for that is the state is available, right? Like we can go look at the state of the contract because it's stored in there, publicly available. It's already on the blockchain. So we don't need to do any computation. We're just querying and viewing a state. So that's completely free to do. So that's why when I click X here, I get this instantly and it gives me 21 because I don't need to actually have a transaction mined to view the state. The only transactions I need are when I'm modifying the state of this contract, okay? Or performing some type of computation. Anyways, what I want to do now is change the contract so we can actually update the value of X. So this is where we'll talk about functions/methods. So what I can do is inside of this contract, I can create a function. This will be a kind of a method associated with the contract. Obviously, I need to give this a name. So I'll give it something like setX. Now for the parameters of this function, I need to define first their type and then the name of the parameter. So I'm going to say uint underscore X like that. This will kind of be my new X value that I want to set X to. Then I need to give my access modifier for this function. Now the access modifiers essentially tell people trying to use the contract if this function is private, if it is public, if it's internal, external. I'll talk about what all of those mean, but you need one of these here. So I'm going to say public to define the fact that anyone can use this method. So a contract, anyone calling this from a transaction is able to use this method because it's public. Same with this variable X. Now, if we made X private, for example, you wouldn't be able to access the state of it, at least not very easily, because it would be private to the contract. Again, we'll talk about access modifiers in a second. For now, though, we'll just say function set X uint underscore X. We'll make this public. Then I'm just going to say X is equal to underscore X. Okay, so now when I call this function, we will change X, change the value, and then when we access it again, it will be different. Pretty straightforward. Okay, so now that we've changed the contract, we need to redeploy this. I'll do this again to the Gorelli test network, so I'll just click on deploy. Okay, we're going to have to confirm the transaction, and notice this time it's a bit more expensive. We have more content in our contract, and so it makes sense. This is going to be more expensive, right? So I'm going to click confirm. Okay, it's going to take a second, and then once it's created, we should be able to use it, and I'll show you what happens when we actually modify X. Okay, so the contract has been created. I'm going to click right here. And now we'll have a new contract, so we'll look at that one in a second. But for now, what I can do is set X. So if I look at X right now, it's 21. That was free, right? I didn't have to pay for that. I'm just viewing the state. But now if I change the state to say 25, so let's set X, notice I need a transaction, okay? So it's giving me a transaction, and this is going to cost me a certain amount of gas, right? So I will click confirm. Now this is going to take a minute. I need to wait for the transaction to be mined. Okay, it was done pretty quickly. Now if I click X again, its new value is 25. So I've modified the state of this contract. Okay, hopefully that makes sense. That kind of wraps up all the explanation in terms of how you call a contract, what the state of the contract is, all of that stuff. Now we're going to continue looking at some more Solidity syntax. All right, so I've just cleared my code and changed the environment back to JavaScript VM. Now I'm going to talk to you about a few data types in Solidity. So the first one is uint. Now we've already looked at this. It stands for unsigned integer, meaning we can store any positive whole number, okay? So I can do something like uint public X is equal to 1. Of course, we know that is valid. Now with the uint, this actually allows us to specify the number of bytes we want to use to store the integer. So I could do something like uint 8, uint 16, uint 32, uint 64, uint 128, and then 256. And I believe 256 is actually the default. So if you just write uint, I think by default it uses 256. I'll put something on the screen that confirms that or not. Now let's actually just see what happens if we try to store a negative number inside of a uint, okay? So let me just deploy this contract here. We have our smart contract, and notice that it's actually not even deploying this, right? Because we would have seen the variable y because we have an error. So it's deploying the last contract, so the last one that we actually had compiled, not this one because we have the error and it's showing that right here, okay? We cannot implicitly convert -1 to an unsigned integer. Now, of course, though, we have regular integer, right? So a regular int allows us to store a signed number. Again, just like the uint, we can specify the number of bytes. So 16, 32, 64, whatever. Now let's run this one. So deploy, and let's see what we get here. And now we have y. So it actually deployed this contract and we can look at its value. Perfect. Okay, so that is int. Now, other than int, we have a Boolean. Okay, so we can say something like Boolean public y is equal to true. Let's deploy this. Now, oops, I want to close that. Let's look at this contract here. Click on y and notice we get true. Now, of course, other than true, we have false. I assume most of you know what the Boolean data type is. Just note here there is a lowercase on the first letter rather than a capital if you're coming from Python like me. Okay, so we had int, uint, bool. Now, we also have address payable, and mapping, and a ton of other data types as well. Now, I'm only going through these ones because these are kind of the core, most important ones we're going to use right now. There is strings, there is arrays, but those work really strangely in Solidity compared to other languages. So just be careful there if you're looking at, say, a string or an array. There's a lot of nuances and kind of details with those. Okay, for now, though, let's actually not do a string. So let's actually just look at the mapping type. So the mapping type allows us to take some key and associate it with some value. So I'm going to say public, and then we'll just call this map, okay? Now, what this means is that I can have some data type for the key and some data type for the value. This is very similar to a dictionary or a hash table. So when I define a mapping, I need to pick the value for the key, or the type, sorry, for the key, and the type for the value. So for right now, I'm just going to say uint, like that, is associated with int. Now, just to show you how this works, what I can do if I want to set a new mapping is I can say map, and then I can put my key like this is equal to my value. So if this was a real example, I could do something like maybe the map of 1 is associated with the key of -2. Now, that means if I accessed map at 1, it would give me -2, okay? So this allows you to associate some key with some value. Very useful. You're going to use this all the time. Anyways, that is a mapping. Again, you put the type of the key, and then you do this little equal and I guess greater than sign or less than sign associated with whatever the value data type is. So right now, what I'm going to do is just make a function that lets us actually add a new key value pair to this mapping. So I'm going to say function, we'll say set key like that. We're going to take in a uint key and we'll take in an int value. Okay, and then we're going to say that this is public. And inside of here, we'll just say the map at key is equal to value, okay? Now, since this function is actually going to be changing the state of this contract, that means we will require a transaction to use this, excuse me, but since we're in the JavaScript VM, we don't need to do that because we're not actually on the blockchain. Anyways, let me quickly go through the syntax. So function keyword, this lets us make a method or a function inside of the contract or inside of the class, whatever you want to call it. We then have set key. This is the name of that function. We have our parameters, key and value, and we're defining the type that is required for those. We then say this is public, meaning anyone can call it. And we say map key equals value, adding a new key value pair to our mapping. Okay, let's deploy this. Okay, so here's our contract. Let me open this up. So we have set key and map. Now, one thing to note is that automatically when you define a variable like this outside of a function, so just in the body of the contract, it's going to have a getter added for it automatically, which means I can access any value in the map. So I could do something like map1, and we're going to see its default value is 0. So in Solidity, all of our data types have a default value. So even though we didn't assign this to something, we just declare that it exists. If I try to access any key, since the value type is int, it's always going to give me 0 unless we have a different value for that. Okay, so let's just set a key. Let's set like 5 with, actually, let me do this. We'll set 5 with like -23. I'll click on transact. And now to test this, I'll see if the key 5 is associated with -23. And it is, so we're all good to go. Now let's do another one. Let's do like 4 with -10. Okay, transact. Let's go 4. And then notice we have -10. Perfect. There we go. Okay, so now that we have done that, what I want to do is talk about addresses and how we actually accept money in the contract as well as pay money out. So let's get rid of all of this for right now, and let's start making some functions that can receive money and send money. So what I'm going to do is write function. We're going to call this receive, and this is going to be an external, like this, payable function. Now let's talk about external because we haven't yet seen this. So just like the public keyword that we had, what external does is it makes it so that this can only be used from outside of the contract. So I cannot call this function from within the contract. If I did that, that would give me an error. And the reason for that is because we're going to be accepting some Ethereum. And when you define this as payable, which is what I've done right here, this means that we can actually pay money to this function when we call it, okay? Hopefully that makes a little bit of sense, but we're saying function, receive, external payable, meaning, okay, we can accept money and we can only accept money from outside of the contract. So we can't call this from within the contract. Whenever you're accepting money, you need to put payable. When I say money, I'm really talking about Ethereum. Anyways, inside of here, we actually don't need to do anything. We can just write the body of this function. In fact, that's completely fine. And now what I'm going to show you is that what we can do is send money to this contract by calling this receive method because it's external payable. So what I'm going to do is deploy this. Okay, when I deploy it, I'm going to have my contract down here, and we have this receive function. So when we click this red button here, what's actually going to happen is we're going to send this amount of whatever this unit is, so in this case, it's way, from this account to our contract, okay? So this function doesn't need any body. If it's external payable, that just means we can pay money to it. And so what I'm going to do here is set this to like, I don't know, we'll go with 10,000 way. Now, way is the smallest amount of Ethereum that you can send. I believe 10 to the 18 way makes 1 ether. So this is a very small amount. Anyways, it's going to take it from this account. In fact, let's just send it from another account so that we can see if it actually worked. Let me make it a bit larger. And when I click the button again, it's going to send that amount from this account to the contract. So let's do that. And now notice this amount has gone down. I have sent some way, right? There you go. Makes sense. Now, there was also some gas associated with that. That's why it's not perfectly even. And the gas limit was right here. Okay, awesome. So we said function, receive, external payable. Now, this contract technically has a certain balance. It would be 10,000 way. All right, so now that we've looked at that, I'm going to show you how we can actually view the balance of this contract from a function. So I'm going to say function, and then this is going to be get balance. Okay, let's spell balance correctly. And then we don't actually need anything inside of parentheses. And what I can do is make this a public view that returns like this, a uint. And sorry, not unit. This is going to be a uint. And then we can actually write the body of our function. Now, let me just talk about this view keyword because we haven't seen this yet. View is saying that this is a read-only method or a read-only function, which means it cannot modify the state of our contract. So you need to add that when you're writing a function that's going to return a value that's not modifying the state, okay? That's what we're doing. So public view returns uint. Now inside of here, what I'm going to do is I'm going to simply return the address of this dot balance. Now, let me talk about this for a second. So return, I mean, pretty straightforward. We're returning a value from the function. Now, what address is doing is actually casting this, which is referring to the contract itself to an address. So this is the address type, right? We can use this to actually cast this, the contract, to the address. And then on the address type, we have balance. Balance is how much ether is in this account, or in this case, in this contract. Now, previously, you could just write this dot balance. However, in the new version of Solidity, what you need to do is manually cast this to an address. So again, this is just giving us the address of the smart contract. We're then getting the balance and then returning it. Awesome. So let's deploy the contract and see if this works now. So I'm going to go here. I'm going to send some money to this contract. First, actually, I'll go get balance. When I run get balance, notice that we have 0, right? There's just 0 balance. And let's now send some money. So let's go from this account here and let's just send 1 ether. Okay, so if I send 1 like that, let's click receive, click on get balance, and then notice it's going to give me the balance in way, okay? If I wanted to convert that to ether, I would need to divide it by 10 to the 18, way, or I guess I could just divide it by 1 ether. Anyways, not super important. Point is that, there you go, that is how you get the balance. Okay, so now that we've looked at that, I want to talk to you about a few global keywords that we have access to in Solidity from our smart contract. So remember, whenever the smart contract is running, it's been initiated, whatever, it would have had to have been called from a transaction. So someone had to send the transaction, they had to call a specific function or method, and then maybe they sent some ether along with that. So we actually have a way to access that information, like who sent the transaction. So what I'm going to do here is write a smart contract that keeps track of the last person to send it ether. So I'm going to make a variable up here. I'm going to say this is an address. Now, again, the address is just storing an Ethereum account address, right? Or the address for an Ethereum account. So that's the data type there. We have access to things like .balance on an address. So I'm going to say address. This is going to be public. I'm going to say this is last sender. So let's go last sender like that. And for now, we'll just make this equal to nothing. Okay, so it'll have a default value. I believe the default address is just a bunch of zeros. Okay, then inside of receive, I actually want to set this to be equal to whoever the last sender was. So I'm going to say last sender is equal to, and then this is where we talk about the global keyword message.sender. So message is something that you can use to access all of the information about the transaction that was used to call this contract. Now, other than message.sender, we also have access to message.value. Now, this is going to be the amount of Ethereum that was sent with the transaction. And we have access to message.gas as well. So the amount of gas, I believe, that's remaining with this transaction. Okay, so let's go and change this back to message.sender. And now we can actually use this smart contract and see if it keeps track of who sent the Ethereum. So I'm going to deploy this. Okay, so we should be deployed. Let's change to one of these fresh accounts and let's actually send 1 ether in the receive here, okay? So I'm going to send that 1 Ethereum. Let's check the balance. Okay, now the balance, oh, sorry, this is wrong contract. I want to use this contract. Okay, let's send 1 ether. Okay, so go receive. Now let's check the balance. Okay, so we have 1 ether in here. And now if I go last sender, it gives me the address of the account that actually sent this Ethereum. So now let's change this to be, let's go with this account. Let's send 2 ether. Okay, get the balance. We now have 3 Ethereum inside of here, and the last sender has now changed. Okay, there you go. That is how you keep track of the actual last sender of Ethereum. Now what I would like to do is I want to show you how to send Ethereum from the contract back to a different Ethereum account. Okay, because right now what's happening is we're sending Ethereum to the contract, but the contract's not sending anything back. Obviously, that's not ideal. We need a way to, pay people back from the contract. So let's do that. So what I'm going to do is write a function. I'm going to say function. This is going to be pay. This is going to be address, payable, ADDR, and then this is going to be public like this, and then payable. Now, let's just quickly go through this. So the reason I have the payable here is because whenever I want an address or whenever I want to be able to send Ethereum to an address, I need to specify it as payable. So address payable is different than just regular address. This actually allows me now to send the money to this account. If I don't have payable, then I won't have access to the methods I need for this address to send the money to. So just make sure you put payable. Then we're going to have public payable. Now, since this function is going to be paying money out, it's payable. If you're going to be sending money or receiving money, you need payable. And then, of course, this is public, which we've already talked about. So inside of here, there's a few different ways that I can actually send Ethereum. Now, some are simpler than others. Unfortunately, though, there's a bunch that have kind of some issues with them and that are not recommended to use. So the ones you should not use are the following: ADDR.transfer. Okay, now I know I spelled that incorrectly, but you should not be using transfer. Okay, there's some problems with that. I'm not really going to get into them. And then we have .send. Again, there's some problems with this. Don't use this. Instead, what you need to use is the most complicated one, funny enough, which is going to be something like this. So let me just type it out, then I'll explain it. This is going to be bytes, memory, and then this is going to be data. And this is going to equal to ADDR.call. And then we're going to say here that the value is equal to and whatever the amount of Ethereum is we want to send. And then we're going to call this with 1 argument. Okay, I believe this is correct. Let me move this over a bit so we have some more room. Okay, so function pay, address payable, ADDR, public payable, and then we have this kind of crazy line right here. So first of all, what this is going to do is it's going to decompose the return value of this into 2 variables. First, sent, and then second, bytes memory data. Now, this first one right here is going to be a Boolean variable telling us if this was successful. So if it was successful, this is going to be true. Otherwise, it's going to be false. There's a variety of reasons it could be unsuccessful. One of them being you don't have enough money in the contract to send. Okay, then we have bytes memory data. Now, this is going to give us the data of this transaction. Now, you don't really need to worry about this too much. In fact, I'm not really going to explain it, but memory is specifying that we want to store this data, which is a reference type, in memory. Again, I'm not really going to talk about this much more. Just write this for now. We'll worry about this in a later video. Then what is this doing? So what we're doing is we're saying address.call, okay? And then inside of curly braces here, we're passing the value, which is the amount of Ethereum we want to send. Now, optionally, we can actually choose the amount of gas that we want to send as well. So forward with this transaction. You don't need to do that. You can just leave it to the default value, which is what I'm going to do. And then we call this whole thing with a string. Now, this is going to be the message that's going to be sent to our, to our transaction or with our transaction. So you don't really need to put anything here for right now. It just requires one mandatory argument. So that's why I put in empty string. Okay. Hopefully this makes a bit of sense. Again, address.call, curly braces with the amount of Ethereum that you want to send. And then this is setting up the transaction, and this is actually going to execute it when you do the kind of parenthesis call right here with the string argument. Anyways, what we can do after this is we can check if this was successful or not. And the way we do that is we could use an if statement. So ifs do exist in Solidity, right? I could do something like if sent, or I can use this fancy thing that we haven't seen yet called require. Now, what require does is similar to an assert statement because it's going to check the value of a condition or a variable. And if that's true, we're going to continue. Everything will be fine. If that's false, it's going to throw an exception and actually tell whoever called this smart contract that there was an issue with that call. So I'm going to say require sent, and then here I can put an error message. So I'll just say error sending money, okay? Like that. Or error sending, let's just go with F. Okay, so again, if this is true, all is good, we will continue. If this is false, then it's going to tell us that there was an error because we were unsuccessful in sending this Ethereum. All right, now let's add our semicolon, and what I can do is deploy this and test it out. Okay, so let's go back here, and let's deploy this. Let me close this contract. Okay, so we have our deployed contract. We have pay, receive, get balance, and last sender. So let us receive some money first. So let's send 1 Ether from this account. So let's go receive. Okay, last sender is this. Get balance is 1. Now let's copy this guy's address right here by clicking on copy. Let's paste it in here. Let's click on pay. And I think everything should be good. We can go back here now and we can see if we were paid the Ethereum or not. All right, so I thought something was going wrong until I realized that we actually are only sending 100 way here rather than an entire Ethereum, which is what I thought we were going to be sending. So what I'm going to do is change this to 1 Ether. Now, Ether is actually a built-in word or a built-in keyword in Solidity, and it will just multiply this by 10 to the 18. So that will give me, I guess, 10 to the 18 way, right? So 1 Ether. Anyways, I'm going to change that to 1 Ether. So now this will pay 1 Ether from this function. Okay, so let me redeploy here and let's close this. Okay, and now we have our contract. So let's receive some money. So let's go from this account. Let's just send like 5 Ether. Okay, so let's go receive. What's the balance? 5 Ether. Now let's copy one of these. Okay, and we'll pay it. And let's see if this is all good. I'll move up the console and looks like it's sent fine. Okay, so now let's go here and we should see that in one of these accounts we have, okay, almost 101 Ether, right? So I have 100.99999 because there was gas associated with the transaction. So we didn't get a full 1 Ether. We got a little bit less. Perfect. There you go. That is how you send money using, I guess, this right here, using this line. Okay, great. So now that we have that, what I want to do is I want to end by quickly writing kind of an example of a bank that allows people to send Ethereum to this smart contract and then withdraw up to the amount of money that they had sent to the contract. So if I send 1 Ether, I can withdraw up to 1 Ether from the contract. As soon as I try to withdraw more, it's going to tell me, hey, you don't have a sufficient balance. So kind of just like a very simple bank account. So let's go ahead and do that. All right, so let's get into this example of implementing kind of the basic bank accounts. So I'm actually just going to get rid of all of this. We can just rewrite it. This will be good practice. So I'm going to start by making a mapping, and this mapping is going to allow me to associate an amount of Ethereum with an address. So that way I'll know how much a specific account has sent so far, and so I can regulate how much they can withdraw. So what I'm going to do here is say mapping, and this is going to go address like that, and then this will go to an unsigned integer, which will be the amount of way that they have sent, so amount of Ethereum. Okay, then I will call this balances. And I can actually manually make this private if I want. Now, when I make this private, what that means is there won't be a default getter for this, so I can't easily just access the balance of a specific account. Instead, I'll have to use one of the methods or functions that we define. Okay, now we need some way to receive money, so let's write that. We're going to say function, and we'll say deposit, okay, and then this is going to be actually external, and then payable. Okay, now what I'm going to do is I'm going to say balances at, and then this will be message.sender, which is going to be the address of the sender of the transaction, is equal to, or sorry, plus equal to message.value. Okay, so remember all of the keys here are going to have a default value of 0. So even if this address doesn't kind of exist yet in the balances, it's going to have a value of 0 when I access it. So I'm going to add message.value, which is the amount of Ethereum they deposited. Okay. Then, of course, if this already existed, I would just be adding to it whatever the amount of Ethereum is they deposited in this transaction. That's all I need for here. I'm just adding this to the balances. Then what I'm going to do is say function withdraw. And this is going to need to take in an address to withdraw to. And in fact, I don't necessarily need to do that because what I could do is just use the message.sender address. So whoever was withdrawing, whoever sent the transaction, I just automatically give the money to them. But instead, what I'll do here is just put in an actual parameter so that you could technically withdraw your money to someone else's account. Hopefully that makes sense, but you'll see what I mean. So I'm going to say address, payable, and then this will be ADDR. And then we'll say this is going to be a public, and then this will be a payable function like that. Okay, so what I need to do here is I need to check that they have a sufficient balance in the balances before they can withdraw something. I also need to take in the amount that they're going to withdraw. So I'm going to say uint amount like that, and this will be the amount in way that they want to take it. Okay, so we'll say withdraw, payable, amount. Okay, great, that's fine. Now inside of here, what I'm going to do is I'm going to confirm that they have a sufficient balance before I let them withdraw. So I'm going to say require, and I'm going to say balances at ADDR is greater than or equal to the amount that they want to take out. Okay, perfect. So we'll do that. Then I'm actually going to send the Ethereum to them that they want to withdraw. So we are going to say, I guess this is going to be bool sent, and then this will be byte memory, and then what was this, data is equal to, and then ADDR.call, and then this is going to be value colon amount. Okay, and then I think I can just call this like that. Okay, so that's good. Now that I have that, I'm going to confirm that they sent it successfully. So I'm going to say require sent, and we'll say could not withdraw. Okay, we got to spell this properly. This is just, okay, there we go. Could not withdraw. And then what I'm going to do here, after I successfully check if they withdrew or not, or after I check that they successfully withdrew, I'm going to subtract their balance. So I'm going to say balances, and then this is going to be at message.sender minus equals the amount. Okay. I think that should be good. Now let's just run through this and make sure we understand. So first, we're requiring that their balance is greater than the amount. So if the balance that they currently have in our kind of bank here is not greater than the amount, then we actually need to give them an error message, and we'll say insufficient funds like that, okay? I think that's how you spell insufficient. That should be fine, all right? And then what we're doing is we're trying to actually send this amount to them. So if they have a sufficient balance, we'll try to send it to them. If this for some reason does not work, then we'll tell them that they could not withdraw, and we'll keep the balance here, right? Because if we didn't send it, then the balance is not gone. We still have the money in the contract. Otherwise, we will subtract their balance, and then we're good to go. Okay, so now we have deposit and withdraw. And if we want to, we can write one more function here. Let's go function get balance, and this will just give us the balance of a contract. Okay, so let's just go public view returns uint. Okay, and then let's return the address of this dot balance, and that should be good. Okay, now we could also write something that allows us to get the balance of a specific address, or we could just make this public, but for now I'm going to leave it private. Okay, hopefully that is all good. Now what I'm going to do is just deploy this contract. So let's deploy it. Let me get rid of this one. Now what we can do is deposit some money. So let's go to this account. Let's deposit 10 Ether. Okay, so we're going to deposit. That should have happened successfully. Let's check the balance. Looks like we have 10 Ether. Now let's see if we can withdraw. So let me copy this address. Okay, so I'm going to paste that in there. In fact, let's make this larger. And for the amount, I wish I could copy this. Let's just go with a bunch of zeros here. I don't think I can write F directly in here, otherwise that would be useful. Okay, so let's click on transact and let's look at our console here and see if this was good. Okay, it looks like we successfully sent the way. So now if we go, we see we have 85 Ether rather than 84, which is what we had before. So let me see if I can make this something like 5 now and click transact. Okay, it looks like that was successful. I guess we're not passing enough zeros. Okay, now we have 85.5999. Okay, now let me try to send an entire 5 Ethereum, which we know we don't have for this person. Actually, maybe we do, because I think we transacted 10 Ethereum. Sorry, but let's try this. Okay, transact, and that was successful. Now let's try this again. And notice that when I try to do it again, I don't have enough Ethereum for this balance, so I get insufficient funds as my error message. Okay, and if I look at the balance of here, we have 4.4 Ethereum left in the contract. So now let's try to do this from another account. So let me copy this address. And let's see what happens if I try to withdraw, say, 1 Ethereum from this address. Okay, if I do that, notice we get an error. It says insufficient funds because this address has not yet deposited any Ethereum. So let's now deposit some. So let's make this 1 Ether. Let's click deposit. Okay, now let's try to withdraw. And notice we were able to withdraw that successfully. All right, so that is all I have to show you for this example here. Hopefully that was a decent introduction to Solidity. I understand there was a lot of stuff covered in this video. I don't expect you to know all of it. I just wanted to kind of show you how to create a basic smart contract, how to send Ethereum, receive Ethereum, and then hopefully give you a bit of an idea behind the theory of how smart contracts actually work. In the next video, we're going to continue learning more about Solidity. I'm going to show you some more advanced things that we can do. And then in future videos, we'll talk about some of the limitations of Solidity and how to make things more affordable using Cartesi, which is a sponsor of this video and this series. Hope you guys enjoyed. If you did, make sure to leave a like, subscribe to the channel, and I will see you in another one. Hello everybody, and welcome to another video in this Blockchain for Beginners tutorial series. In this video, we're going to be continuing from the last video and learning more about Solidity. Once we learn a few new topics, then we're actually going to work on an auction where we're going to be auctioning an NFT. Now, this will work with any type of NFTs. This is really, really cool, and if you're interested in NFTs, you're going to learn a little bit about how they work. So with that said, we'll get into the content in a second, but I do need to thank Cartesi again for sponsoring this video and this series. They are an awesome company. They've been helping me come up with the content for this series, and they have a bunch of scaling solutions for Ethereum and for developing smart contracts that we're going to look at in a future video. Regardless, let's go ahead and get into the content. All right, so I am back in Remix, and in front of me I have the example that we finished in the last video, which is kind of a mock bank account. Now, what I'm going to do is just give you a quick recap of everything that's in this contract so we understand the syntax and get a quick refresher. Then we'll look at some new Solidity features, and we'll actually move into working on that auction, which is going to be the bulk of the video. Okay, so right now we can see we're inside of a .sol file. Now, the .sol stands for Solidity, and that's the extension you need for your Solidity smart contracts. Now, at the top of our contracts, we need a pragma line. Now, the pragma line is going to tell Solidity what compiler version we should use. So in this case, we're using 0.8.10. To see the compiler versions, you can go to the Solidity compiler extension, click here, and then it will show you the versions. In this case, 0.8.10 is one of the latest, so that's the one that we're going to use. Great, we then define our contract. We say contract my contract, open the curly brace and close the curly brace, and inside of here is the content of our contract. Now, it's worth noting that you can define multiple contracts in one Solidity file, and you can have stuff like contract inheritance. That's a little bit complicated. We don't need to look at that here, but just wanted to mention that. Okay, so inside of our contract here, we start by defining what most of you would consider a class attribute. This is just going to be actually a private member of this class because we've defined it as private. Anyways, this is a mapping type. Now, the mapping type is like a hash table or a dictionary where we have some key that can be associated with some value. Now, in this case, we're having an address. This is going to be an Ethereum address being associated with a uint, so an unsigned integer. We then denote this as private, meaning we can't directly access this from outside of the contract. And then we have balances. That's just the name of this mapping. Okay, now we have a function. The function is called deposit. It's denoted external and payable. Now, external says that we can only call this function from outside of the contract, so I couldn't go here and do something like deposit. That would be invalid because this is an external function. Then we have payable. Payable is saying that this is either going to be sending money to someone or receiving money, or specifically Ether. And in this case, since we're going to be getting money, we have to make it payable. Then what we do inside of deposit is we say balances at message.sender. Now, message.sender is going to be the address of the sender of the transaction who's sending money to this contract. So essentially, whoever invoked the call to this contract or made the transaction to this contract, it's going to be their address. We're adding that as a key to balances, and then we're going to increment the value here by message.value. Now, message.value is going to store the amount of Ether that they sent to this contract, and the reason why we can do this is because the default value of all of our uints inside of our mappings is going to be 0. So even if this sender does not already exist in the mapping, we'll simply make the value equal to whatever the message.value is because the default value is 0. Hopefully that makes sense. That's explained in the previous video in case you are confused. Regardless, we now have withdraw. So withdraw is going to take in an address payable. This is going to be our ADDR. That's going to take in uint amount. Now, this means that we need to pass an address to this withdraw function. This is the address that we want to withdraw funds to. Then we have uint amount. This is the amount of funds that we want to withdraw from the contract. Now, this is a public payable function. When we say this is public, that pretty much means it can be called from anywhere. And then we have payable. And again, what payable means is we're either going to be sending money out or receiving money. So of course, we need to denote this function as payable. Okay, we then have a require statement. Now, what the require statement is going to do is it's going to check if this condition is true. And if it is not true, then it's actually going to raise an exception. And the exception is going to be insufficient funds. That means we're actually going to cancel the entire contract call. Everything that would have happened is going to be reverted. I'm going to talk about this more in a second. And essentially, this transaction is going to fail because this condition was not satisfied, okay? So you use require when you want to ensure that something is true before proceeding in the contract. Okay, so we're requiring that the balance of the address is greater than or equal to the amount that we want to withdraw. Makes sense. If we don't have that, then the error or the exception is insufficient funds. So next, we're actually going to send money from the smart contract to this address if they had sufficient funds to withdraw. So we're going to say bool sent bytes memory data is equal to ADDR.call, and then we're putting the amount that we want to withdraw, and then we're actually calling this transaction. Now, if you're confused on how this line works, I spent about 3 or 4 minutes explaining it in the last video, so you can go back and watch that. Essentially, all this is doing is sending money to this address. This is the amount of money that it's going to be sending, or the amount of Ether. Great. Then we have this bool sent. Now, this bool sent is going to be equal to true if we successfully sent this. Otherwise, it's going to be equal to false. So if we were not able to successfully send the money, some error occurred there, then we're just going to raise the exception could not withdraw. Otherwise, what we're going to do is we're going to update the balances. So we're going to say balances at message.sender minus equals the amount to make sure they can't just keep withdrawing the same amount of money. It's actually going to subtract from their current balance when they withdraw. Great. Then we go to this function. So this is get balance. Now this is a public view function. Now again, public means we can call this from anywhere, and view actually means that this is only going to be returning or accessing state from this contract. It's not going to be modifying it. So this means we can call this get balance function without actually having to make a transaction, which pretty much means this is free to call. So this is a good point in time to remind you that whenever we're just accessing the state of a contract, this is free. We can just query the state of the contract. We don't need to pay for this. However, if we're going to be actually modifying the state, then that requires a transaction. That transaction needs to be mined. And well, that means it's going to cost us some money, at least in gas and potentially Ethereum, if what we're doing requires that we send Ethereum. Okay, so let's continue explaining this. We then have returns and then uint. Now, returns is just stating what this function is going to return. We're saying uint, standing for unsigned integer. And then here, all we're doing is we're returning the address of this. Now, this is just going to be the contract. We're just going to cast this to its actual address. And then we're going to get the balance. Whenever you have an address, you can access the balance by just using .balance. There you go. That is everything that we did inside of this contract. So now that we've talked about all of this, I just want to spend a second talking about exceptions because we've seen them in this contract, but I haven't actually talked about exactly what they do and how they work. So in Solidity, we have a few different ways to actually throw an exception or to cause an exception to occur. Now, an exception is pretty much an error that's going to occur in our program, and all exceptions in Solidity are state reverting. Now, what that means is if there's ever an exception at any point in time during the transaction call, then this is going to revert the state back to what it was previously. Any changes you've made up until that point will be completely removed. So just to give you an example here, let's say that I did something like balances at 1 is equal to 2. Now, I know this makes no sense, but let's say I did this right here. And then I come to this require line, and this actually ends up raising an exception because sent is equal to false. Well, if that's the case, this line will be completely reverted. We won't actually have done that operation. It will be undone and reverted back to what it was before. So just worth noting, whenever an exception occurs, any of the state in the contract that's been changed is going to be reverted. Now, require, as I'm kind of alluding to here, does cause an exception, right? So if the condition here is not true, then it raises an exception, and the message for that exception is going to be whatever we put here. Now, there's a few other ways that we can raise exceptions in Solidity. I'll quickly show them to you, although we're not really going to look at an example of them. So one way to raise an exception is to use revert. Now, revert actually allows us to just directly revert the entire contract state. Again, this is just going to raise an exception exactly like require will, except inside of here, we can just put our error message. We don't actually need to put any condition. So if we ever encounter a revert in the program, we're just immediately going to raise an exception. The exception message will be this. And again, that's going to revert the state because that's what all exceptions do in Solidity. Okay, so that's revert. Now, another thing that we have is assert. Now, assert is similar to require. In fact, it works in the exact same way, except it's designed to be used when you want to check invariance rather than checking input validation. So I'll show you here. I could do something like assert true is equal to true. Now, of course, that's always going to be true, but you get the idea. Now, if this condition was false, what would happen is we would raise an exception with this as the error message. Now, assert and require are pretty much identical, but the reason you use assert is because you're checking an invariant. If you don't know what that means, don't worry about it. And if we're using require, we're using that when we want to check input validation, okay? So that's why we're using require here, because we want to ensure that the amount that they passed in is valid. Now, in this case, we could probably actually replace this require with an assert. It's not a huge deal, and there's actually not really any formal recommendation on which one you should use, but it's kind of the standard to just use assert when you're checking an invariant and require when you're checking input validation. So in this case, based on what I'm saying, we would use assert here because this is an invariant, but we also can just use require like I had before. That's completely fine. Anyways, this isn't super important, but I just wanted to show you those methods in case you see them in other contracts. All right, so that's almost everything for exceptions. One more thing to note here is that the only thing that will not be reverted if an exception occurs is low-level calls like this, addr.call. Now, I can't really show you what the other calls are because we haven't seen them, but essentially, if you were to send money to someone successfully, and then later on in the contract, there's an exception that occurs, that's not going to be reverted. You just can't revert that because once the funds are transferred, well, you can't really just transfer them back. And so if I did something like this, and let's say that this was successful, then that means this is not going to be reverted. Now, everything else will be reverted. This balances will be changed back, but this isn't going to be reverted. The Ethereum that was sent to that account is not going to be sent back to the smart contract. Okay, there's some good reasons for that, but that's worth noting. Now, a few other things to mention here with exceptions. Exceptions are cascading. Now, that means if I have an exception that occurs in another smart contract that I'm calling from this smart contract, that's going to mean that the state of this contract, as well as the state of the other one, are going to be reverted. So it's kind of hard to show this, but let's say I make a contract and I call this my contract 2 like this, and let's just make some function. So we can do something like function test, and then just make this public view returns uint, okay? And then maybe what I do here is I just say revert, okay? So that's what I do. Now, if I call this function, okay, from inside of here, then even though it's happening inside of this contract, the exception's occurring here, it's going to cascade into this contract, meaning that if any of the state was changed inside of here, that's going to be reverted, and same with any of the state inside of my contract too. Hopefully that makes sense, but just keep in mind that exceptions cascade. So even if you have like 10 contracts all calling each other, and then in the 10th contract an exception occurs, every single one of the contracts that we're dealing with that contract are going to get the cascading exception, and all of them are going to have their state reverted and the transaction will fail. Now, just to note here, the reason why we're getting this error is because I didn't have the semicolon. Of course, revert is fine. I can put this here, although this doesn't really make much sense because why would you just revert inside of a function? All right, so now that we've talked about exceptions, what I can do is start showing you some new features in Solidity. And the first thing I want to do is show you a constructor. So I'm just going to clear everything that's inside of this contract, and I'm going to write a public variable here. So I'm going to say, let's go with address, and this is going to be public, and then I'm going to say that this is the owner of the contract. So what I'm going to show you is a constructor. Now, a constructor is simply a special function that's a part of a class, or in this case, a contract, that's going to be called when the contract is initialized. Now, in Solidity, your constructor will be called exactly one time, and just like any other language constructor, you can accept parameters in here, you can do some setup steps, and well, you'll see how this works. So the way you implement a constructor in this version of Solidity is constructor, open and close parenthesis, open and close curly brace, and then inside of here, you can do whatever you want. So in this case, I'm just going to say my owner is equal to the message.sender. Now, the reason I'm doing this is so that I can keep track of who actually created this contract. So when I create a contract, I have a message.sender, whoever sent the transaction to actually create the contract. So this is perfectly valid. I can say my owner is equal to the message.sender, and now whoever deployed the contract will be the owner, and I'll be keeping track of that inside of this public variable on the contract. Okay, pretty straightforward. That's how that works. Now, again, this is how you do the constructor. You can only have one of them, and this will be called exactly one time and only one time when the contract is deployed. This isn't going to be called every single time a transaction is sent to the contract. It's only called when it's deployed the very first time. So let me show you how this works. Let's go and actually deploy this to the JavaScript VM. Let's click on deploy. Okay, we have our contract. When I click on owner, it's going to give me the address of this account right here, which is the one that I'm using. Now let's try deploying from this account. Okay, so deploy, my contract's down here. Owner, now it's giving me the other owner. Pretty straightforward. That is how the constructor works. And this is a pretty common thing that you'll want to do is keep track of who actually deployed the contract. Now, another thing that you can do in here is accept parameters. So maybe I just want to accept a uint, and let's just go with something like test for now. Again, this can really be anything. Okay, so I want this to be test. And then what I will do is say uint public, and let's just go with, I don't know, v. I'm just picking random names for now, and I can do something like v is equal to test. That's completely fine. I can access the value of this parameter. So now let's get rid of these contracts. All right, so now we can deploy our contract, and notice where the deploy button is, it's actually giving me a parameter that I need to pass here. It's saying test, this is a uint 256. So I'm going to do something like 2, hit transact. Now I go to my contract, I have owner and I have v, and I can see v is equal to 2. There you go. That is the basics of the constructor. Now, of course, you can have multiple arguments if you would like, or multiple parameters, sorry, and do whatever you please with them. Great. So what I'm going to do now is just get rid of everything inside of here, and I'm going to start talking to you about a new thing, which is called a pure function. Now, we've looked at view functions, we've looked at payable functions, internal functions, external functions, public functions. Now we want to look at pure. Now, a pure function is pretty straightforward, but it is simply a function that is not going to do anything with the state of the contract. You can kind of think of it like a static method because it has no access to the internal state of the contract. It just does some type of computations, then returns some value. So I'm just going to write a function here. I'm going to say function, and this will be something like add to. Now we will make this a public, and then this will be pure function. And this is going to return a uint like that. Now I'm going to take as a parameter here the uint x, and all I'm going to do is just return like this x plus 2, okay? Very straightforward, but this is a pure function. Now, as I said, a pure function is not going to modify or access the state of this contract. It's just going to be performing some type of computation that doesn't rely on the actual contract internal state. So just like accessing the data from a contract, this is going to be free as well. We don't need to pay to do this. And let me prove this to you. So if I go to my injected Web3 now, I'm connected to the Gorelli test network, and I deploy this. Okay, it's going to ask me for a, I guess, transaction, because when I deploy, I need to pay for that. And then let's give this a second. Okay, we can see that our contract is deployed. Now let's do something like add to 5. Notice it gives me the value 7 back. I didn't need to add a transaction to be able to do this, okay? So whenever you have a view or a pure function, these are free. You don't need to have a transaction to call these. So if you ever just want some type of utility functions associated with your contract, then you make them pure. Okay, hopefully that makes sense. That's all I need to cover with pure. Okay, so now that we've gone through that, we can start getting into the important stuff, which is events. So I'm actually going to hop over to the drawing tablet to explain to you what events are, and then we'll start implementing them when we work on the auction. All right, so I'm now on my drawing tablet. I'm going to start explaining events to you, but before I can do that, I need to talk to you about why we need them. So in front of me, I have a smart contract. Now this is going to be our auction contract, and on the auction, we're going to have some function called start. Now, of course, we're going to have some other functions as well, but for now, just imagine we have start. And what start is going to do is it's going to attempt to start the auction, so it's going to modify some of the state, and then it's going to return a value indicating to us whether or not this was successful. So we're expecting this to be a bool. Let me just write this right here, indicating that it's going to return a bool. Okay, that's great. So now we want to start the auction. So let's say we have some account. So account 1 like this. We know since this is going to modify state, we need to make a transaction to the auction to be able to start this. So I'm going to make a transaction. We're going to call start on here. And then what we're expecting is that we're going to get some return value here indicating to us whether or not this started successfully. Well, if we're just working on our JavaScript VM, then we know that this is actually going to work successfully. We're going to be able to get a return value. We'll see something like true, or we'll see something like false. However, if we're working on a real blockchain, we're actually not able to return something from a function that's modifying the state back to our account. So essentially, whenever we're making a transaction, we can't return data back to that transaction. Now, this actually makes sense if you look at how transactions work, but for now, you really need to understand that if you ever make a transaction to a smart contract, that contract cannot return you any data. Now, it can try, it can have a return statement, but you're not going to be able to view that return data from the transaction. So really, we have to imagine that this is going to be a one-way operation where we're just going to call start. Now, if an exception occurs, we're going to be notified of that. However, if an exception doesn't occur, we're not going to get any return value. So trying to do something like this is not going to work on a real blockchain. Now, that's a pretty big problem, right? Because in a lot of situations, when I make a call or I make a transaction, to my smart contract, I probably want to get a return value. I need some information. I want to know if this started successfully. However, we can't have a return value. So how do we get around this problem? Well, the way we get around this problem is with events. So what a smart contract can do is it can actually emit events. Now that means that what we can do from auction is when we start this, we can create or emit something known as an event. And this event can have a return value that we might want this account to be able to see. So we can emit an event that says something like started. And then maybe we can put the time that this started at, and we can put if it happened successfully or not. So we can put true, or alternatively, we could put false. Now, these events will be stored on the blockchain. However, they're going to be stored in a different way than the data associated with your contract. So any of the variables you would have defined or kind of the state of the contract is said to be in storage. These events are not going to be in storage. They're going to be stored as a part of the transaction history on the blockchain. So that makes them a little bit less accessible. However, they are much cheaper to use because of the way that they're stored. So I'm not going to get into this too much, but essentially just understand that your events are stored in a different way that makes them much cheaper to actually store, although they are a little bit harder to access. So that means that you usually use a third-party tool, maybe something like Etherscan, to actually read and query these events because it's not as simple to go directly look at them like it is for the data on the contract. And so we emit this event, and then this account here, or some external client that's off the blockchain, is able to view these events and subscribe to them so they'll be notified if an event occurs. Now, I'm going to get into a detailed example in a second, but for now, just understand that whenever we have a transaction, our smart contract cannot return a value to that transaction. Instead, what it can do is emit an event. This event will be stored off the blockchain. You can kind of think of these events as a log, right? We'll be able to then view those logs off of the blockchain, and we can search for specific data inside of those logs and subscribe to events, which means we'll be notified when an event occurs. Now, just an important note here, this is not the case. So the no return value thing is not a case if we're making a call not a transaction. Now, I understand this is a bit confusing, but if I'm making a call to a function that does not modify the state, so that doesn't require that I spend money on it, doesn't need a transaction, essentially, I'm just querying the state, then of course I can get a return value, right? If all I want to do is just get some data that's stored in the state of the auction, that's fine. I can do that. I can get a return value. But if I make a transaction that modifies the state, that's the situation where I can't get a return value. Okay, hopefully that makes sense, but that is why we need events. So now let me clear the screen and let's get into a more advanced example. All right, so for this example, what I want to do is imagine that we're trying to build an application that's going to be partly on the blockchain that's going to allow us to auction our NFT. So again, we still have this auction, this is our contract, but now what we probably want to do is we probably want to make a nice, beautiful user interface that allows users to interact with this auction. So to interact with the auction, the owner of the auction is going to need to start it. And then once it's started, we're going to be able to accept bids, right? Now the bid will be a certain amount of Ethereum, and we'll need to keep track of what the current bid is, who's currently winning the auction. We need to know when the auction ends, and all of that logic, again, will be handled by auction. However, we want a very easy way for users to be able to interact with the auction contract. I don't want them to have to write some really low-level code and send their own transactions. Instead, I want them to just be able to connect their blockchain account or their Ethereum account with my user interface and click this nice big button that says bid, okay? So they're going to be using my user interface. All of my clients are going to have a different instance of the user interface. Maybe this is something like a React app or something like a JavaScript client, whatever, right? So let's say we have kind of two user interfaces here, and we have two people that are bidding against each other just for simplicity. So I'm going to say that this is number one and this is number two. Now, the concept here is that this person's going to press the bid button, it's going to send a transaction to the auction, it's going to send maybe 1 Ethereum, and well, that's going to be their bid. And then this person, maybe they want to send a bid, maybe they send a bid of 2 Ethereum. Now, this is all great, but again, we run into this problem where I want these user interfaces to be able to be updated whenever another bid occurs. So essentially, if I'm sitting right here, I want to know that number 2 just made a bid so that I can then bid again, and I can bid 3 Ethereum, right? Now, how do I do that? Well, since I can't get a return value here, and since my auction can't send something to my user interface, it's not able to do that, what I need to do is use my events. So what's going to happen is every single time I make a bid, an event is going to be emitted. So I'm going to say emit, and then I'll emit an event that's going to be something like, let's write this properly, something like bid 1ETH, and then it will be from number 1, and then it will probably give the time that this bid occurred and a bunch of other information. But the idea is we're going to emit all of these events, and then what we can do is we can have these user interfaces subscribe to the events. So when they subscribe to the events, what's going to happen is they're going to be notified when an event occurs, and then they can use the data from the event to update their user interface and tell the user, hey, you just got outbid. Do you want to bid again? Or hey, the current bid is this, or the auction ended, or whatever. You get the idea, but the concept here is we have an external client, right? So our JavaScript client's kind of sitting on some type of user interface. They are subscribed to the events that this contract is going to be emitting, and whenever the contract emits an event, they'll be able to update their user interface, and they could, say, query the state of the auction if they wanted to. They could do that for free because that doesn't require a transaction. Hopefully this makes sense, but that is the point of events, and this is kind of how you would start building out a very simple blockchain application. You would deploy your smart contract. This would be kind of your source of truth, right? This would handle all of the complex logic. Then you would have your nice user interfaces that allow the user to interact with the smart contract and be updated of things that's happening with the smart contract. Because the smart contract can only do some type of operation when a transaction is performed, so you need some type of external client sitting, listening for events, and updating the user. Then the user can trigger those transactions to the smart contract when they actually want to do something that is state changing. Perfect. There we go. We now understand the importance of events. Let's go ahead and go back to the computer. We're going to start writing out this auction contract and looking at events. All right, so I am back on my computer in Remix. We're actually just going to start working on the auction contract, and then as we work on that, I'll show you events. So I'm going to change the name of my contract here to auction because that's going to be a bit more fitting, and I'm going to implement a bunch of public things that we need here for our auction. So if we're thinking of an auction, we're going to have a time span for this auction. So we need to know if the auction has been started, if it's ended, how much time is left, so when the auction is actually going to end. We want to know all of the bids. We want to know who's selling the NFT. We want to know what the current highest bid is and who the current highest bidder is. And we also need to know what NFT we're selling, but we'll deal with the NFTs later because that's a little bit complicated. So for now, what I'm going to do is say address payable. It's important we do payable here because we're going to want to pay this person who you'll see is the seller. So we're going to say address payable public seller. Now it needs to be payable because, well, the seller of the NFT, we're going to have to pay the profits of the auction. So whoever, the highest bidder was, we're going to take money from them and send it to the seller. Okay, now other than that, we are going to need to know when the auction started. So actually, we don't need to know when it started. We just need to know when it's going to end, if it started, and then if it's ended. So I'm going to say bool, and then this will be public, and this will be started. We'll then say bool public ended, and we'll say bool, or sorry, not bool. This is going to be uint, and then this will be public, if we could spell this correctly, and then end at, and this will be the time that we actually are going to end the auction at. Now, other than that, we need the highest bidder. So we're going to say uint, or sorry, we want the highest bid. So I'm going to say uint public, and then this will be highest bid, like that. And then we will have address. And do I want this to be payable? Let me look at my cheat sheet here. No, I don't think we need that to be payable. We'll just say address public, and then highest bidder, like that, and that should be good. Now, other than that, we're going to need some mapping to keep track of all of the bids that users have made to this contract. So the idea here for the auction is that when you make a bid, you have to send money to the contract. So if you don't actually end up winning the NFT, then you need the ability to withdraw your money, right? So we're going to have a withdraw function that allows you, if you didn't win, to actually take all your money back from the contract. So I'm going to say mapping, and then this is going to be address, and this will go to a uint, and this will be a public, and then this will be bids. Now, the reason all of these are public is because I don't need to hide any of this information. It's fine if everybody sees it, and I want people to be able to see when it started, when it ended, what the end at is, what the highest bid is, because you want people to trust this contract. That's the whole point of writing smart contracts, right? Okay, so now that we have that, I'm going to make a constructor. I'm going to say constructor like this, and all I'm going to do is simply assign the seller. So I'm going to say the seller is equal to message dot, and then this will be sender. So whoever deployed the smart contract will be the seller of the contract. Now notice I'm getting an error here. It's going to tell me that the type address is not implicitly convertible to expected type address payable. Now, I didn't show this to you previously, but the way that you can convert a regular address to a payable address is you can just say payable like this, and then surround what you want to convert. So now this address that is not an address payable will be payable, and I'll put that inside of seller. Okay, now what I'm going to do is implement a start function. This function will allow only the seller of the NFT to start, and they'll need to pass all of the NFT details to be able to start the auction. Now, we won't implement the NFT stuff right now. As I mentioned, we'll do that at the end. So I'm going to say function. We'll just call this start. Then this will be public external. Okay, so we're going to call this from outside of the smart contract. And inside of here, what I want to do is I want to require that the message.sender is equal to the seller. Otherwise, I will say you did not start the auction, exclamation point, okay? And then we'll go with semicolon. Now, what's the error here? It says visibility already specified as public. Okay, so that's my bad. Sorry, I'm just going to make this external because you can't have public external. Those are going to be, messing with each other. So external is fine. Now, what's the warning? Function state mutability can be restricted to view. Okay, that's fine. We're going to change that later. Okay, so now what I'm going to do is I'm going to say started is equal to true. And then what I need to do is pick the end at date. Now, this is going to be a little bit weird because we haven't seen this yet, but I'm going to say end at is equal to, and this is going to be block dot, and then timestamp plus, and then 7 days. Now, we can actually change this so that it's not days. And in fact, let me check if that's correct. Okay, actually, I think 7 days is correct. So first of all, let's just explain what this line is because I haven't covered this. So block is actually referring to the block that this transaction is a part of once it's been mined, right? So once it's been mined, it will be a part of a block, and the block is going to have a timestamp. That's when the block was created. So this is going to give us the relative timestamp of the transaction. It's not going to be precisely when we sent it, but it will be very close to that because blocks are created very, very quickly in Ethereum. And then we're going to add 7 days to that. And days is a keyword just like Ether in Remix. So I can, or sorry, not in Remix, but in Solidity. So this way, we're just going to add 7 days to this timestamp, which means we will end 7 days after this. So of course, feel free to modify the number of days. I mean, you can make this 1 day if you want, 2 days, whatever. It doesn't really matter. In fact, let's just go with 2 days for now. But whatever you set this, that's going to be the amount of time the contract, the auction will last for. Okay, so now we have start. However, what I want to do is add one more require here that just makes it so we cannot start this contract if it's already started. So I'm going to say not started like that. And then I'll say already started exclamation point. And what I want to do is I want to emit an event saying that I started the contract. So now we're going to talk about how we actually implement events. Now, creating an event is actually pretty straightforward. You first need to declare an event in the body of your contract. So I'm going to do it up here. I'm going to say event and then start. And I've just created an event. Now we need to emit these events, but this is an event that is emittable. So what you do is you put the keyword event, you then put the name of the event. In this case, I'm going to go with start. Now notice I'm starting it with a capital because the convention here is Pascal case, just like our contracts. And then inside of the parentheses, you put any arguments you want the event to accept. So you could put, for example, the address of the person who started the event. Now that wouldn't really be very useful because the only person who can start the event, start the contract or start the auction is going to be the seller. But you could put any other data you want here. You don't need to put the time because that will automatically be associated with events whenever they're emitted. But I can put any data inside of the parentheses, and then I pass that data as arguments when I emit the event, and that'll be like the data of the event. We'll see this in a second. Right now for start, I don't need any arguments, so we won't look at that right now. But when I do events for a bid, I'm going to have the address of the person who bid, the amount that they bid, etc., right? Okay, so anyways, we have an event defined, which is start. And now if I want to emit an event, this is really straightforward. I just do emit, and then I put the name of the event like that. Okay, there you go. I'm now emitting the start event. Now, if start was accepting arguments, I would pass them right in here. So whatever the arguments are, right? Okay, there we go. Pretty straightforward. So now that we have that, let's deploy this contract. Let's deploy it to a legitimate network, right? So I'm going to deploy it to the Gorelli test network, and then I'm actually going to go look at the events of my smart contract and show you how you can view them off the blockchain on Etherscan. So let's do this. I'm going to click deploy, and then once it's finished, I will let you know. Okay, so the contract has now been deployed. So I'm going to click on the contract deployment here. I'm going to view this on Etherscan. Notice it says that it was successful. So what I'm going to do now is click right on the contract. So notice it says contract here. It was created. So I'm going to click on that. And when I go here, we can see we have the hash of the transaction that created the contract. Then I can click on events. Now, when I go to event, notice we don't see any events. Now, that's because we haven't triggered any yet, but I'm now going to trigger an event and show you that it will show up right here. Okay, so let's go back to Remix. Let's now go to our contract, and let's start by just clicking on some of these so we can see the seller. Is it started? No, it's not started. So let's start it by clicking on start. Now, when we do this, of course, we need a transaction because this is going to modify the state. So I'm going to click on confirm. Okay, this is going to take a second to complete. And let's just go here, and it should tell us when this is done. Then we can go check the corresponding event that would have been emitted. Okay, so this is finished now. So let's go back here, and let's refresh the page. And notice that we have an event. Now the event is start, okay? And I can click on this right here and kind of view some of the details. Now the method will actually be the method that we called in the transaction. Now this is going to be a special hash of this method. I'm not really going to describe exactly how you kind of read this stuff because there is a special way to do that. However, whenever you're going to be subscribing to events or trying to get the data associated with an event, you're not just going to be reading it from this page. You're going to have a client. This client's going to be using a special library. A library could be something like Web3.js. This is a JavaScript library that kind of handles a lot of this complex lower level stuff for you, and it will kind of decode this data and tell you the stuff in the event. Now, I'm not going to show you how we subscribe to events in this tutorial because it's fairly complicated, but if you were writing, say, a JavaScript client or something, what you could do is use something like web3.js. So let's do this. This is the Ethereum JavaScript API. And inside of here, you can subscribe to events. So if we go to eth.subscribe, this is the thing right here. I'll leave a link to this in the description, and you can kind of view how you would do this and how you actually get the data associated with events from a smart contract. Okay. Let's go back to Remix though, and let's continue. All right, so now that we've written the start method, let's write the end method or the end function. So I'm going to say function end external, and inside of here, I need to require a bunch of things. The first thing I'm going to require is that they started the contract. So I'm going to say require started because, well, if they haven't started it, they can't end it. So I'll say you need to start first, exclamation point. Doesn't really matter the error message that I give. Then I will also require that the block.timestamp is greater than or equal to end at, because I don't want to allow someone to end the auction if the end at time is not yet reached, right? Because that would be unfair. That means you could have someone like bid on it and then you could end it for them so that they would win it before anyone else was able to bid. Anyways, we're going to do this. We're going to say block.timestamp greater than or equal to end at. I'll say auction is still ongoing. Is ongoing one word or two word? I think it's one word. Someone can correct me in the comments. Clearly, programming is greater than spelling. Anyways, and then we also want to make sure that it's not already ended, right? So I'm going to say not ended. We'll say auction already ended. And let's spell already correctly. Okay. Exclamation point. Perfect. So now that we have all of our requires, what we can do is say ended is equal to true. And then we want to emit an event that says we ended it. Now, of course, when we end, we're going to actually have to transfer the NFT to the highest bidder, and then we're going to transfer the funds from the contract to the, the seller of the NFT. But for now, we'll just do the events. So let's go up here and let's say event and let's say end. Now for this event, I actually want to know what the highest bid was and who the highest bidder was, so I know who won the auction, right? So I'm going to say, let's go with address, and this will be, I guess, highest bidder, okay? And then we will go with uint, and then this will be highest bid, okay? So that's for event. And in fact, I guess I can do this. Yeah, that's fine. We can do that inside of here. Okay, so now for end, I'm going to say emit, and then end, and then inside of here, I'm going to pass the highest bidder. So let's go highest bidder like that, and then let's pass the highest bid. Perfect. Okay, there we go. Now, one thing I want to add to start is I just want to add a parameter here that's going to be the starting price or the starting bid or whatever for the auction. So I'm going to say uint, we'll say starting bid. And what I'm going to do is after I start this, or it doesn't really matter where I do this, but I'm going to say that the highest bid is equal to, and then this is going to be the starting bid. So this way, you're going to have to bid at least a little bit higher than this to be able to actually win the item if you were, say, the only bidder. That way, someone doesn't list this and kind of get screwed by only having someone bid like one way or two way or something and no one else actually bids on the NFT. Regardless, we'll have that for now, and we can now test if end is going to work, and then we can implement bid, and we can implement withdraw, which are the other two functions that we're going to need. So let me save this. Now let's close this. I'm going to deploy the contract again. This will take a second. Once it's done, I will be back. All right, so the auction is now deployed. Now I can start this by passing, say, 1,000 way as the starting bid. We will wait for this to go through, and then we can try to end it. Now, I will show you that when we end it, this isn't going to work. Now, the reason it's not going to work is pretty obvious, but we don't have this condition being equal to true, right? The block.timestamp is not going to be greater than or equal to end at, so it's not going to let us end this, and I'll just show you that that works in a second once this starts. Okay, so that's started. Let's now go to this contract. The way I'm going to get to this is I'm going to open up MetaMask. I'm going to go to contract creation. Okay, let's go here. Let's view the contract. Okay, it's still indexing. Let me refresh this. Once it's done, I'll be right back. Okay, so now it is fully successful. Let me click on the contract. Let's go to events, and we can see that the event start has been triggered or been emitted, right? Because we started the contract. So now let's see what happens if we try to end it. So notice it's going to tell us that we're probably going to get a problem here. It's saying that gas estimation errored with the following message. See below, the transaction execution will likely fail. Do you want to force sending? And it's saying that the error's auction is still ongoing. So it's actually able to look at our smart contract and realize that we're not going to be able to do this because the block.timestamp is not greater than or equal to the end at time. So we can still send the transaction if we want. Now, if we do this, what's going to happen is it just going to fail? Now, when it fails and we hit a require statement, the require statement will return whatever remaining gas we had as a part of this transaction back to us. However, some gas is going to be lost. Now, that's one thing to note here with require. It does actually return your gas if this fails. Again, not all of it because it still had to use some gas, but it will return whatever wasn't used. So you can see here we're getting this error, right? It's telling us this didn't work, and we weren't able to do that because this require statement would have been, well, not true, right? It would have, caused an exception. Okay, so hopefully that makes sense. That is how that works. Now that we've done that, let's start implementing the bid and the withdraw functions that we need. Okay, so let's code out the bid function. Let's go with function bid external. Now this needs to be payable because this is actually going to accept Ethereum, right? So inside of here, we need to require a few things. We're going to require that we have started the auction. If we haven't started, then obviously we can't do this. So I'm going to say not started. We're going to require that the block.timestamp, again, this is a global keyword that we have access to, is going to be less than the end at time. So this means that the contract is not ended, or sorry, I keep saying contract, I mean auction. So we'll say ended, exclamation point. And then we will also require that the message.value, so this is going to be the value of the bid because they're going to be sending the amount of the bid, right, is greater than, and then this will be the current highest bid. Okay, so now we have all of our require statements. Now let's see why it's getting mad at us here. It's saying expected semicolon, but got identifier. Okay, I need a semicolon right there. So now if this is the case, what we're going to do is we're going to update the amount of money that people have sent to this contract, kind of similar to the bank account by using this bids mapping. And we're going to update the highest bid and the highest bidder because at this point we know this person would have bid an amount higher than the highest bid. So we need to update those values, right? So we're going to say that the highest bid is equal to message.value. And we're going to say that the highest bidder is equal to the message.sender. Okay, so now after updating this, since the highest bidder has now changed, what I need to do is make it so the person who just got outbid is able to withdraw their money from the contract. So I'm going to say if, and then this is going to be the highest bidder. So not bid, but bidder does not equal the address 0. Now, address 0 is the default address. I'll talk about this in a second. Then what I'm going to do is say that bids at, and this is going to be highest bidder plus equals, and then the highest bid. So the logic here, why is this yelling at me? Let's see what the problem is. Operator not compatible with types uint 256 and address. Sorry, this needs to be highest bid, not highest bidder. Okay, that's better. But the logic here is that as soon as someone gets outbid, I want to allow them to withdraw their money from the contract so that they could withdraw and then bid again, right? Because otherwise they would need to have a ton of Ethereum to be able to actually continually outbidding someone if all of their money is stored in the contract. So hopefully this makes sense, but since we're updating the highest bidder now, if the highest bidder was not equal to address 0, so essentially if this was not the first person to make a bid, then what we do is we take whatever the highest bidder was, store that in our bids mapping, and then we add whatever their highest bid to that so that now they're able to withdraw. And let's say they don't withdraw and they just continue making bids. That's fine. This will continue to increment however many bids they've made. So then they will be able to withdraw all of that if they're not currently the highest bidder. Okay. And actually they'll be able to withdraw whatever amount inside of there is not their current bid that's being stored in highest bid. You can look through this logic and probably see why that makes sense. But address 0, just to clarify here, is the default address. So when I write something like address public, for right now, sorry, not address public, but address public highest bidder, it's going to be storing just a 0 filled address. So I'm just making sure that it's not equal to the 0 filled address. And you can do that by just writing address and then putting 0 inside of here. Okay, so that is bid. That's pretty much all we need for bid. Now we want to write the withdraw function. So I'm going to say function withdraw like that. And then this is going to be an external payable as well. And inside of here, what we need to do is withdraw a certain amount, or I guess we'll just withdraw the entire amount of whatever the person's bidded that's not the current bid. So we're just going to start by getting the amount of money they've sent to this contract that's not currently the highest bid. So I'm going to say a uint, and I guess I'll just go with something like balance is going to be equal to, and then this will be bids at message.sender. And then what I'm going to do is say bids at message.sender is equal to 0, just to reset that. And then I'm going to send whatever their balance is to them. So the way I'm going to do this is I'm going to write this complex line. In fact, I'm just going to copy this in because we saw this in the last video. I'm going to say bool sent bytes memory data is equal to payable message.sender. So just converting that address to a payable address dot call value. And then this is going to be balance. Balance is right here, right? And then what I need to do is require that this was successful. So I'm going to say require sent, and I'm going to say could not withdraw. So let's do this. Could not withdraw. Let's add our semicolon, and there we go. We have just implemented the withdraw function. Now what I'm going to do is actually add some events here as well for bid and for withdraw. Then we can test this out, and then we'll start actually working with an NFT because right now we're not really auctioning anything. So let's make some events. Let's make an event for bid. Now what I want to do is have an address. Now this is going to be indexed. Now we haven't seen this keyword before, but what you're allowed to do whenever you're defining the arguments for your events is you can put an indexed parameter, and you can actually put up to 3 of these, and this is what you will be able to search for an event for. So if I say indexed here, then this means I can search by whatever this parameter is for this event in my logs, right? Or in my events. So I'm going to say address indexed. Let me just look at my cheat sheet to make sure I don't mess this up. It's going to be sender. And then we're going to say uint amount to specify how much they actually bid. And then we'll do an event, and this is going to be withdraw. And this again will be an address that's going to be indexed. This will be the bidder. And then this will be uint and the amount that they withdrew. Okay. I think that is fine. Now, what's it telling me? What's it saying I did wrong here? Oh, I spelled index incorrectly. Okay. So let's go and let's now emit these events. So I'm going to say emit, and then this is going to be bid. And then we're going to pass to this just the highest bidder and the highest bid. Okay, perfect. Let's add our semicolon. And then for withdraw, we will say emit and then withdraw. And then we're going to emit the message.sender and the balance. Great, there we go. Okay, so now let's actually just deploy this. We can do some experiments with it. I'll set up another Ethereum account, make sure it works, and then we'll talk about the NFTs. So I'm going to deploy. Once it's done, I will be right back. Okay, so I am back. This finished deploying. My contract is here. I actually started the contract with a minimum bid of 1,000 Wei. And now what I'm going to do is change my Ethereum account. In fact, I've actually already done this. So I deployed this contract from my tutorial account, but now I'm on account 1. So now I'm going to make a bid from account 1 and show you how this works. So I'm on account 1. You can see I've reconnected this here to, Remix. And now I'm going to make a bid of 1,000 Wei. I'm going to click on bid. Then when I do this, notice it's going to tell me that I'm probably going to get an error. The reason I'm going to get an error is because this is not greater than the starting bid. And so I'm just going to cancel the transaction. So I'm going to change this now to be 1,001. Let's click on bid. And let's see. Okay. So confirm. Let's give this a second. And again, notice I'm not going to get any return value here. It's not going to tell me if this was successful or whatever. I'm just going to see that the transaction didn't fail whenever this is done. And then I should see an event be emitted here. Okay, so let's now refresh this. And we now see, okay, maybe we need to wait a second. Okay, so the event has showed up. I just had to wait a second. I was being impatient, but after I refreshed a few times, it appeared here. Anyways, this has happened successfully. I know this looks like gibberish, but if you were actually subscribing to this event, then you would have some library that would be translating this for you, so you'd be able to read the real data. Regardless, the bid happened, and I can look now at, for example, the highest bid, which I can see is 1,001, the highest bidder, which is this address. I can look at the seller, which is different, if the contract is started, and all of this type of stuff. Now, that's pretty much all I wanted to show you for that. Since we don't really have 2 days to wait here for this to finish, I can't show you it actually ending. What I will do, though, is I will now start implementing the NFT stuff, which is a little bit complicated, but it's pretty cool, so I'll try my best to explain it to you. All right, so I've just switched tabs, and I'm going to try to explain to you the difference between fungible and non-fungible tokens and how these kind of live on the Ethereum network. So I'm sure all of you are familiar with cryptocurrencies, right? We have currencies like Ethereum, we have currencies like Bitcoin, and we have a ton of other currencies that are built on top of these main blockchain networks. So if we're talking about coins that are built on Ethereum, these are tokens. Now, really all a token is a smart contract that defines that your address owns a certain amount of tokens. Now, this is specific to Ethereum, but if you're working with a token that's on the Ethereum network, really what gives you the ability to own that token is that there's a smart contract with the name of that token. It's named, say, Timcoin, for example, right? If I had my own token on Ethereum, and in that contract, it says that your address has 20 Timcoins or 100 Timcoins or whatever it is. Now, the way this all gets standardized is that what happens is you need to implement specific methods or specific functions on your smart contracts that make it act like an ERC20 or an ERC721 token. Now, ERC20 is simply a protocol for a specific token. In this case, it's a fungible token. Now, ERC20 states that you need to define some special methods on the smart contract. Now, if you do that, Ethereum is able to look at your smart contract and treat that smart contract like a token rather than just any other smart contract. Now, that means in your Ethereum wallet, you're going to see your tokens showing up, or you'll be able to link them. You'll be able to then say buy these tokens or exchange these tokens because you've defined certain functions on the token and it meets the ERC20 protocol. Hopefully that makes sense. Now, ERC20 is simply a fungible token protocol. What that means is every single one of these tokens is exactly the same. So there's no difference in you owning one of the tokens or the other tokens. Like any token is just identical. Each of them has the same value. And as it says here, this makes ERC20 tokens useful for things like medium of exchange, voting rights, staking, whatever. Okay, that's what you can use these tokens for. However, now we go over to ERC721. Now, ERC721 is fungible tokens. Now, fungible tokens mean that these tokens are different. So there could be a different value associated with each token. Maybe there's some assets like an image associated with a token, hence NFTs, right? Maybe you get some special rights with a specific token. Tokens are unique, they are different, and they have a unique ID. Now, this is very similar to ERC20, except you're just having these unique tokens, and you have some special functions now that you need to define on smart contracts that are defining an ERC721 token. So it's a little bit too complicated for me to show you exactly how to create your own NFTs or your own ERC20 tokens, but the concept is, again, that we have this smart contract. This is an example of an NFT contract. This smart contract defines who owns what NFTs. It's capable of creating new NFTs. And then if I wanted to say, send my NFT from me to you, what I would do is call a function on the smart contract that transfers the NFT. I have to be the owner of the NFT to be able to do that. And then it changes the internal state of the NFT contract to now define that you own my NFT because I sent it to you. So hopefully this makes a tiny bit of sense, but that's the general idea behind tokens and behind NFTs and all of this type of stuff. Now, as you can see here, there's some other types of tokens that you can create, but ERC721 is the one we're going to work with right now. And what we're actually going to accept in our smart contract that's going to be the auction is the address of a smart contract that represents an NFT, as well as the unique ID associated with the NFT that the user wants to auction. So whenever you get an NFT, it has a unique ID associated with it because every single ERC721 token is unique. When I say ERC721, that really just means non-fungible token, okay? And so it has a unique ID. If I pass that unique ID along with the contract representing that NFT, then what I'm able to do is verify that the user owns that NFT and then actually list it in the auction and transfer it between different people. Okay, so now let's get into some even more complicated stuff because I need to show you how we can make our own NFT. And when I say make our own NFT, I'm not talking about make your own NFT contract. I'm saying kind of acquire an NFT in your Ethereum account so that you can follow along and actually auction off your own NFT in this tutorial. All right, so to do this, I'm going to go up to this other tab here where I have token.sol. Now, I'm not going to explain any of this code, but essentially this is my own Timcoin NFT, okay? And I'm going to give you guys all the privilege of owning some Timcoin completely for free. It has zero value and it's going to be on an Ethereum test network, but you can own it for free. You are welcome. And the way I'm going to do that is I'm going to deploy this smart contract. I'm going to leave a link to the contract address in the description, and you actually are able to create your own NFT by calling this award item function, which is going to give you your Ethereum address, a NFT, okay? It's going to give you a special ID essentially of Timcoin. I'll explain this more in depth and I'll show you exactly how to do this. But right now, when you're watching this video, this will be deployed on the GoRally test network. So you need to make sure you're using that test network. And then what you'll be able to do is interact with this contract from Remix. Again, I'm going to show you exactly how to do that. It will then award you an NFT. And then once you have that NFT, you'll be able to auction that NFT inside of our test contract. Now, before I show you how to do that, we're going to implement kind of the NFT logic in our contract. Then I'll show you how you get your own Timcoin NFT. Again, you're welcome. You guys can thank me in the comments. Okay, so what we're going to do is we're going to now specify what's known as an interface that we are going to accept for a specific contract, which is going to be the contract address of the NFT that we want to list. So I'm going to say interface. So actually, there's not a ton of value of me typing this in, so I'm just going to paste in the interface and I'll explain what this is. So first of all, an interface is an abstract data type. The reason we're going to use an interface is because we need to verify that the contract passed to this auction does actually represent an NFT. And so we're going to treat the contract as an IRC 721 type contract, which means we're going to make sure it has a transfer and a transfer from function on it. Now, if you're unfamiliar with interfaces, I can't explain them too much in depth. Essentially, they just enforce that anything that is of type of this interface has these methods that are specified in this way. So for us to have a valid NFT contract, really all we care about is that it has a transfer and a transfer from function that we can use. Now, the transfer from allows us to transfer from one address to another address, a specific, NFT ID, okay? So as I was saying before, all we're doing is we're going to be calling a function on the NFT contract that takes in the address of the owner of the NFT, the address of the receiver of the NFT ID. It verifies we own this NFT, and then it would transfer it to here. And then transfer is simply going to take an NFT ID and transfer it to a specific address once it's been approved to do that. You'll see what I mean in a second, but anyways, that's our interface. So what we're going to do now is we're going to go inside of our auction, and we're going to define the NFT that we're actually going to be auctioning. So I'm going to say IERC 721 public, like this, NFT. And then what I'm going to do is I'm going to say uint public NFT ID, okay? So what I'm saying is I want to store the contract of the NFT address here. It's going to be of type IERC 721, meaning it has to have these functions on it. And then I'm going to have uint public, not NDT, NFT ID, which is going to be the unique ID of the NFT that we want to auction. So now inside of my start function, what I'm going to do is take in a starting bid. I'm going to take in the NFT contract and the unique ID of that NFT. So I'm going to say IRC 721. This is going to be NFT, and we'll make this underscore NFT. And then we are going to say uint NFT ID. We'll just make this underscore again so it doesn't mirror our global name, and then comma. Now let me make sure I typed that correctly. I think I did. Okay. So now inside of here, what we're going to do is we're going to set the NFT. So we're going to say NFT is equal to, and then this is going to be underscore NFT. Again, this is the contract representing the NFT. Then we're going to say NFT ID is equal to underscore NFT ID, like that. Now, what I'm going to do is just take these two lines here and put them after I do this, just in case these return some error, although it doesn't really matter because if an error was returned, then the state would have been reverted, but that's fine. Okay, so we're going to do that. Now, what we also need to do is we need to transfer this NFT from the owner of the NFT to this contract. So now the contract owns the NFT and then is able to actually transfer this to whoever wins the NFT in the auction, right? So what I'm going to do is say NFT dot transfer from, and we're going to transfer from, and this is going to be the message dot sender, who we're assuming owns the NFT, to this, or sorry, it's going to be address this like that, and then this is going to be NFT ID. Okay, so this here is going to fail if we don't own the NFT. So if whoever called this start here doesn't own the NFT, then we're not going to allow them to transfer because the NFT contract will raise an exception. And so that whole thing will cascade, meaning all of this is going to fail as well. And so we won't actually start the auction. So we're only able to start the auction if we own the NFT and if we have the ability to send the NFT from the sender to this address, okay? Hopefully that makes sense. I'll explain again how we kind of set the NFT up and how we actually make an NFT and get access to it in a second. So now that we have that, what we need to do is deal with what happens when the auction ends, because once the auction ends, we need to send the NFT to whoever won it, and then we need to take the balance of the contract and specifically whatever the highest bid was and send that actually to ourselves, right, to the seller of the NFT. So all we're going to do here is we're going to check if and this is going to be highest bidder, does not equal the address 0, because if it's equal to the address 0, that means no one actually bid on this item, and so we can just return the funds or return the NFT to ourselves. So anyways, we're going to say if this is the case, then that means that we're going to take whatever the highest bidder amount was, or the highest bid, sorry, we're going to transfer that to ourselves, and then we are going to transfer the NFT to whoever won the NFT. So I'm going to say NFT dot transfer, and then we're going to transfer it to the highest bidder. I think that's all I need to put in here. Let me confirm that's correct. Oh, one more thing, the NFT ID. Okay. So we're using the NFT contract. We're using dot transfer. We're going to transfer it to the highest bidder, and then this will be the NFT ID. Now, what's it saying is the issue? It says transfer is not found. Well, that's because I spelled transfer incorrectly. Okay, that's fine. Then after that, we're going to figure out whatever the highest bid was, and we are going to then pay that to ourselves, the seller of the NFT. So the way we do that is we just copy in this line because I really don't feel like writing it again. So we're going to say bool sent, and then bytes memory equals data, seller.call value, and then this is going to be highest bid, and then we'll call that like that. And then we're going to require sent, and we're going to say could not pay the seller. Okay. There we go. Now in the other situation, so if the highest bid actually is equal to address 0, then what we're going to do is just return the NFT to ourselves. So we're going to say NFT dot transfer, and then this is going to be to, I guess we will just say the seller, and then this will be NFT ID. And I think that's it. Again, I spelled transfer incorrectly. Let me just make sure that's right. Looks good to me. Awesome. Okay, so that is actually all we need for this contract. Now, this contract should work. However, I need to show you how we can now actually get access to an NFT and what that looks like in our account. So I'm going to start by deploying this contract. Now, be careful what account you deploy this from. I'm going to deploy it from this one. So I'm going to deploy test.sol, which is really just my kind of auction contract. Let's confirm this. Okay, this will take a second. Once that's done, I will be right back. Okay, so that has now been deployed. Now remember, to be able to start this auction, we actually need the address of our NFT. So I am now going to deploy this NFT contract here. I'll leave the link to it in the description, or you could just painfully write out whatever the number of characters are. But again, it'll be linked in the description, and I'll show you how you can use this to get your own NFT. So let me now deploy this. I need to pass a string name and a symbol. Actually, do I need to do that? Oh, sorry, I'm doing the wrong thing. Okay, let's deploy Timcoin. So I'm going to deploy Timcoin to the Gorelli test network. This is going to take a second, and then I will show you again how we can actually access this and get our own NFT. Okay, so Timcoin has now been deployed. Now for me, I can see Timcoin right here, right? And we see all these different methods. You don't have to worry about a bunch of them. But anyways, you're not going to see this inside of your remix because you didn't deploy this contract. But you need to interact with the contract, again, on the Gorelli test network. You need to be on the Gorelli test network, otherwise this isn't going to work for you. So what you're going to do is you're going to take the contract address, which will be linked in the description, and you're going to paste it right here where it says or at address, okay? So it should say that right at the bottom. You're going to do that, and then it will load this contract. Now notice it just loaded the same contract for me twice because I already had it here. But that's how you can load it. Again, just copy it, paste it in here, and then it will load it right here. Now what you're going to want to do is you're going to want to start by setting the approval for all. Now, I'm going to discuss what this is in a second, but essentially what you need to do here is you need to allow this smart contract, being the auction, to actually transfer your NFT. Now, if you don't allow it to do that, you're not going to be able to actually auction the NFT. The reason you can't auction the NFT is because the contract will not have the ability to take the NFT and transfer it to itself. So you have to explicitly give the contract permission to do that before you create your NFT. So what you're going to do is go to your auction contract. This is going to be different than mine. You're going to copy the address of your auction contract. Okay, I've done that. I'm going to go to Timcoin. I'm going to go to set approved for all. I'm going to paste in my contract like this. And then I'm going to go comma, and I'm going to go true. Now look here, it says operator, which is this. So the operator is the auction contract. It's going to be operating on this NFT, and then true. Now what this is going to do is it's going to allow this contract to pretty much list any of your NFTs. Now you still have to call the contract for it to do that, but you're giving it explicit permission for it to access any of the Timcoin NFTs that you have access to. So don't worry, this doesn't mess with any other NFTs you might have on your Ethereum account. And we're on a test network anyway, so it shouldn't matter. But I'm going to press transact. This should go, or this should be successful once I click confirm here. Okay, so let's wait for that to finish. And then we have set the approval for all of the NFTs that you own to be able to be operated by the auction contract. Again, what you're passing here is the auction contract. Now, it's very important that you do this first before you actually give yourself an NFT. Otherwise, the NFT you give yourself will not have the approval set for it for the auction contract. Okay, so now that we've done that, let's close all of these. And we're going to go to the award item function. Now, this is what you want to press when you want to give yourself an NFT. So you're going to copy your address. So my address is right here. I'm going to copy it in to award item. And then what it says here is that there is a URI. Now, the token URI is actually a URL to JSON metadata related to this NFT. So as you may have seen, NFTs have like fancy images and music and GIFs and all of this very valuable stuff. Anyways, the point is, all of that stuff is stored off of the blockchain on a specific URL in JSON data. And so what you actually have to do is associate data with your NFT off the blockchain. So when I create the NFT, I pass the URL of the data sitting off the blockchain that represents my NFT, and then it links those two together. And that's why when you go and you view NFTs, you see like a nice little fancy image. It's because it's referencing the URI of this NFT, and then it's grabbing the image for it and displaying it. Pretty straightforward, but that's really how NFTs work. Again, it's not meant to be an entire lesson on NFTs, but the token URI is just that, it's a URL. Now, you actually don't need to pass anything here. I'm just going to pass like 1, 2. Like, you have to give some data, but you don't have to give a URL. So I can pass 1, 2, 3, 0, whatever, doesn't matter. So just go like that. And when I hit transact, then what's going to happen is it's actually going to give your Ethereum account or whatever account you put the address for an NFT. So let's wait a second. And then I'll show you that we actually will have Timcoin showing up in our Ethereum wallet. Okay, so that finished. So now if I go to MetaMask, so let's get out of this here. Let's go to MetaMask and let's look at my account. Let's go to assets and notice how it says, don't see your tokens, import tokens. So I'm going to click on import tokens and I'm going to copy in the token contract address of Timcoin. Now, again, that's what will be linked in the description. I can just copy it from right here. So I'm going to go here. Going to go to assets, import tokens. I'm going to paste this in. Notice the symbol is Tim, very fitting. For the token decimal, just put 0 and then add custom token. And now it's showing that I have 1 Tim token. So I'm going to go import tokens like that. And now if I look at my assets, I see 1 Tim coin, okay? It's just looking at the contract, and since it follows the ERC 721 protocol, it's able to specify that I have 1 of these. Now, if you want to own multiple, just do this again. Just call the contract. You can even pass the same URI. It really doesn't matter. And hit transact. And now when you do this, you're just going to have to wait a second, and then your wallet should update. And once this is done, you'll now have 2 Tim coins. And in fact, just because this is interesting, I will show you that if I go to MetaMask, I go to my wallet here, and let's go view account on Etherscan. You can actually view the Tim coins that you have on here. So notice I can go to token, and I can specify Tim coin. And when I go here, you can see that I have the token ID of 1. I have 1 Timcoin that was just added here in 1 minute. Now, if I refresh this, I should have a second Timcoin in a second because I just requested that. Okay, it might take a second. So let's go back to where we were before. Okay, award item, let's refresh. Okay, so now we should have 2 Timcoins. If we go here, yes, there we go. Now we have Timcoins and the token ID is 1 and 2. So if you want to see what your token ID is, because all of you are going to have a different token ID, you need to do what I just did. Go to MetaMask. You're going to view your account on MetaMask. So I went to, where is that? Here, view account on, sorry, not MetaMask, on Etherscan. It's going to bring you to Etherscan. And then what you can do is go to your Timcoins. I showed you how to do that, but let's go back. So you're just going to click here, click on Timcoin. And then it will show you your token ID. So you own token ID 1 and 2. Well, in this case, I own 1 and 2. You'll own something that's not 1 and 2 because it's going to be a unique ID. So this means I can auction token ID 1 and 2 because I own that. So now, how do we auction it? Well, this is kind of the moment of truth here to see if this is all going to work. So I'm going to copy the address of my Timcoin NFT contract, okay? Then I'm going to go to start. I'm going to paste that in as the first argument. So let's go here. For the NFT ID, you have to post an ID that you own. So either 1 or 2 for me, and then put a starting bid. So I'm going to put 1,000, and I'm going to hit transact like this. Okay, fingers crossed. Once I hit this, let's see if this works and if everything we did was successful. Okay, so very good. We see the green check mark here, meaning that this was good. So now let's go to NFT and notice the address is this. NFT ID is 1, seller is me, started is true, highest bid is the 0 address because no one's made a bid yet, and then we have highest bid. Now, of course, this will work as it would work before as we tested it previously, and this will now take, how many days did we set? If we go here, I think we set 2 days. Yeah, so after 2 days, then you'll actually be able to win your NFT when someone hits the end button or sends the end request to this contract. Okay, so that is going to wrap up the video. I hope this was helpful in terms of giving you a deeper understanding of Solidity and smart contracts and showing you a real practical application hosted on the blockchain. Now, in the next videos, we're going to be talking about some of the scaling limitations of Ethereum and of Solidity and some of the problems you can run into when you need to perform large computations. Then I'm going to be showing you some scaling solutions, so ways that you can mitigate those concerns, and we'll be talking about Cartesi, which again is the sponsor of this video and this series, and showing you some of the solutions that they provide. Again, I really hope that you guys have learned a lot from these videos. I've been having a great time filming them, and I look forward to posting more on the channel. With that said, if you enjoyed, make sure to leave a like, subscribe to the channel, and I will see you in the next one. Hello everybody, and welcome to the 5th video in this Blockchain for Beginners tutorial series. Now in this video, I'm going to be talking to you about the limitations of Solidity and of smart contracts and some applications that are very difficult to deploy on the blockchain because of these limitations. Specifically, I'll be talking to you about arrays, strings, for loops, while loops, and why it's very expensive to use those things in a smart contract, and how they can actually cause your smart contract to break or to be in a state where it can never be ran again. I'll get into all of that in this video, but before we dive in, I do need to thank Cartesi for sponsoring this video and this series. As I've said many times, they're an awesome company. I've loved working with them through these videos. They've really helped me come up with a great curriculum to teach you guys. So another massive thank you to them. And with that said, let's go ahead and get into the video. Alright, so I'm now on my computer and I am in Remix. In front of me, I have a very simple smart contract. And what I'm going to be doing in the first part of the video here is talking to you about arrays, strings, for loops, while loops, and then finally structs. Now, after we do that, I'll talk about some of the limitations of Solidities and expenses in using these different features, and then we will talk about some potential, fixes or solutions for these limitations. So let's begin by talking about arrays. So the way you create an array in Solidity is you define the type you would like to be inside of the array for all of the elements. So in this case, I'll say uint. You put your square brackets like this. If you wanted a multi-dimensional array, you do another set of square brackets. And then what you can do after this is put the name of the array or the modifier. So I'm going to do something like public ARR, and then I can just close it off like that. So there you go. I've just now created a dynamically sized array in Solidity. So in Solidity, you can have both a statically sized or fixed sized array or a dynamically sized array. If I do something like this, where I just have square brackets with no element inside or no value inside, this is dynamically sized. So this means it will grow as I add more elements to it. Now, if I do something like 5, this is going to say this array can only have 5 elements inside of it, and I will initialize those elements, I believe, all as 0. All right, so that's the basics for arrays. Now, arrays are a reference type in Solidity, and that means that they are mutable, and we can modify them once they have been created. So we have direct index access. We can access the length of elements, or the length of the array, and again, we can push elements inside. Okay, so let's just deploy the contract right now and have a look at how we actually access the elements in this array. So I'm going to deploy this. When I go here, notice I'm going to have ARR, and then I can pass the index of the element that I want to access. Now, arrays are 0 indexed, so if I do something like ARR and 0, it's going to give me the value 0, because since we statically initialize this array, we're going to have 1 element with value 0, 5 elements with value 0 inside of the array. Now, let's access index 1. Okay, we get 0 again. Let's do index 4, 0 again. Let's do 5. And then notice here that we actually are going to get a revert. The transaction has been reverted to the initial state, and that's because an error would have occurred because we're accessing an index that is out of the bounds of this array. Perfect. So now that we have done that, let's look at how we can actually, I guess, modify the elements of this array. So let's create a function. Let's say function. I'm just going to say mod ARR, standing for modify array. We will make this a public function, and we're not going to return anything. We'll just actually modify this. Okay, now inside of here, I'm just going to take in a uint x and a uint idx. And instead of x, let's actually just go with value, just so this is a little bit more clear. Now, essentially what this is going to do is change the element at index to be equal to value. So let's just say ARR at index, let's go idx is equal to val. Notice we're not getting any errors, so this should be good to go. Okay, so let's deploy the contract. Let's go here. We're going to look at index 0, see that that has value 0. Now let's change this. So let's pass to here a value of, say, 10 and an index of 0. Let's transact. Looks like that's all good. Now when we look here, notice we have a value of 10. Very basic. That's how you can modify this array. Now what I want to do is create a dynamically sized array. So let's simply change this by removing the 5. And now when we do mod array, we're just going to take in a value, and I'll show you how we can append this value or push it to the array. Pretty straightforward, but you can use the .push method. So I can say arr.push. I can push the value, which is uint, and now this should be good. So let's try this. Let's deploy the contract. Let me just delete this one here. Okay, now we have mod array that takes in a value. So let's just pass 1, let's pass 2, and let's pass 3. Now let's look at index 0. Index 0 is 1, index 1 is 2, and index 2 is 3. Perfect, there we go. We just pushed elements into the array. All right, great. So now that we've done that, let me show you how we can get the length of the array. So I'm just gonna say function get length. We'll make this an external, and then this can be a view function that returns, and then we'll just put uint like that. And then inside of here, I can simply return arr.length like that. Okay, so this will give us the length. You can just use the .length property. So let's now deploy this contract. Let's go deploy. Let's mod the array by adding 1, 2, and 3. Now let's get the length, and notice we have a length of 3. Now let's add another element. Let's add 4. Get length, we're at 4. There you go. That pretty much covers arrays. I don't think there's actually anything more to go through with arrays. One thing you can do is access individual elements using the index notation. So I can do something like array at 0 is equal to 1. That's perfectly valid. Or I can just do array at 0. That works as well, as you saw previously. Last thing I will mention is that if you want to actually define the literal for the array, so you want to do something like this, use square brackets. So say uint public arr, and then 1, 2, 3. This is different than something like, I guess, C++ or Java, where you would use squiggly brackets. At least I think you use those in those languages. Anyways, in Solidity, you use square brackets to define the elements in the array. Perfect. Hopefully that is clear. That pretty much covers arrays. Okay, so now that we have gone through arrays, I want to cover strings. So let's get rid of all of this. Now, strings in Solidity are very expensive to work with, and same thing with arrays. Arrays are very expensive as well, and in fact, the reason I'm showing them to you last is because mappings are much preferred over arrays. So you pretty much never want to be using arrays or using strings if you can avoid doing so. There is some use cases where you do need them, but essentially you always want to go with something like a mapping as opposed to an array. I won't get into all of the details, but just understand that they cost a lot more gas than something like a mapping. So if you can avoid it, avoid using arrays. And if you want to mess around with kind of the differences in arrays and mappings, deploy a few contracts and look at the actual gas cost in terms of working with arrays versus working with mappings, and same thing with strings. Strings are extremely expensive to use in Solidity, and one of the reasons for that is that a string in Solidity is actually a bytes array. So you can create a bytes array like this. Now bytes are used for kind of a raw data type, and a string in Solidity essentially is a bytes array that's going to be decoded and encoded with UTF-8, just allowing you to actually view the string. So let me show you what I mean. If I do something like string, and I guess we can put public, although we don't really need to, and we'll just make this equal to a hello. We can say this is equal to world. That is completely valid. Now you want to, again, avoid using strings whenever you possibly can because they're very expensive to work with. Same reason with the arrays, because they are actually represented by a bytes array. Now, strings in Solidity are extremely simple. You do not have index access to them. You cannot concatenate them. You can't get the length of them. There's actually almost no methods or properties for strings. You literally can just store a literal string. And in most situations, it's going to be much more efficient, especially if you're working with large strings, to store them off of the blockchain and simply store a hash of that string in the storage of your contract. That will be much, much cheaper than actually storing the string itself in the contract. Anyways, let's deploy the contract here with the string. Notice that I can access this and I can have world, right? I can see world there. So let's create another function. Let's go function set string, and let's go string, and then let's go with value. Now, I'm not quite done with this yet. I need to talk about something with having strings inside of functions. But for now, I will say hello is equal to val. Okay, so notice that I'm getting an error here. Now, why am I getting an error? This function actually looks pretty valid, right? I have my string parameter, I have this public, I'm setting a value. This should be good. The reason why I'm getting an error here, we can hover over this, is because the data location must be memory or call data for a parameter. So this is where I'm going to talk about the different storage locations that you have in your contract. So in your contract, you have state or storage. They're kind of the same things, storage/state. Now, that essentially means that you're persistently going to be storing this data in the smart contract itself. Now, any data you store is going to cost you small amounts of Ethereum, right? It's going to be more expensive to store more data than to store less. You want to store the least amount of stuff that you possibly can. So that's the first location, storage/state. That's persistent. It's always going to be there. The other location is memory. Now, memory, similar to your computer's RAM, is a temporary location that's only going to be used when the contract is actually executing. So when I'm using a reference type like a string, I need to specify it's going to be stored in memory. So I'm going to say memory like this. So as soon as I put memory, we actually would have seen this before, I think. Now this is valid because it's saying I want to store this parameter in memory as opposed to in the state or storage of the contract. And you only need to specify this for reference data types. So same thing with arrays. Let's say I did something like uint, and then I wanted to have my value like this. I would need to now specify memory to not get yelled at by the compiler. Okay, so let's go back though to what we had before. String memory value, hello equals val. Let's deploy this. Let's look at this. Let's go hello world, I am Tim. Let's set the string. Let's look at hello, and now we have hello world, I am Tim. Awesome. Again, avoid using strings. If you need to use a large string, what you want to do is store it off the blockchain and simply store a hash of that string on the blockchain. That will be much cheaper. Okay, so now we've gone through arrays, we have gone through strings. I want to show you looping, and then I will show you the gas costs associated with a lot of these different features. I'm just trying to give you kind of the basics right now. Okay, so let us, should we loop through an array? No, let's just loop over kind of a range of numbers to start. So I'm just going to say function, and I will say loop, and I'm going to take in uint n, and all I'm going to do here is simply loop over n numbers. So to do a for loop in Solidity is similar to pretty much every other programming language. You can say for, and then you can define your looping variable. So I'm going to say uint I. I'm going to say I is less than n, and then I'm going to say I plus plus. Okay, so I'm just incrementing I by 1 in every iteration. And then what I'm going to do here is, I guess we can just add to some variable or something because I'm just trying to illustrate looping. So I'll do something like uint sum is equal to 0, and then sum plus equals I, and I think that should be good. And then if we wanted to, we could return the sum, but this is fine. We'll just do this for now. So I just had to take a quick cut there because my cat was freaking out at me for some reason. Anyways, that is now resolved, but continuing here, we're getting a warning. The reason we're getting a warning is because this can be restricted to pure. The reason for that is because we're not actually modifying or accessing the state of the contract. So I just want to put pure like this. Anyways, this is how you do a for loop. Now, I will mention that the for loops, again, are going to be very, very expensive to run if you're not doing them in something like a pure function, right? In a pure function or something that doesn't require a transaction, it's not going to cost you Ethereum to run this. However, it's going to be very expensive to implement for loops when you're actually working with the state of the contract. Now, the reason for that is whenever you do a transaction, you need to pass gas along with that transaction, right? And the gas cost is the sum of all of the operations that the contract is doing. So in this case, it's going to cost me gas to actually add a number to another number, right? For me to add two numbers, that costs gas. But here in this situation, the amount of gas this would cost if it wasn't a pure function is n multiplied by all of the gas used inside of the for loop. Now, that might not seem like a lot, but if n is a large number, say like 1,000 or 10,000, and the amount of gas in here is 4 gas, 20 gas, 100 gas, something along those lines, you can see how the amount of gas required adds up very, very quickly, and it becomes unfeasible to actually be able to loop inside of smart contracts. And in fact, there's actually a maximum amount of gas that you can pass to an Ethereum smart contract. I believe right now it's at 30 million gas. In fact, I think that's right here. It's the gas limit that's showing up. Regardless, you can only pass so much gas. So if your smart contract needs to do a ton of computations, you have to have multiple transactions to be able to complete that, because you need to pass the required gas, and you can only do a certain amount of gas in each transaction. Anyways, that was kind of it for for loops. I just wanted to show you the syntax. This is the basics of for loops. Now I will show you while loops. So let's do a very similar thing here. Let's just manually declare I. So uint I is equal to 0. We'll say while I is less than n. We'll say I plus plus. We can do that at the end. And then we'll say sum plus equals I, like that. Perfect. There you go. This is a while loop. Again, not really going to explain this. I'm sure most of you understand how this works. Anyways, those are for loops and while loops. And now that we've looked at those, I want to write a very simple smart contract that's going to work with arrays and for loops or while loops and show you how much gas it actually costs on an Ethereum test network. So let's start by just initializing an array here. And let's just say uint, and let's go ARR. And let's just make this equal, I guess actually I can just define it like that. Uint ARR. That's fine for now. Then I'm going to have a function. I'm going to say function create ARR. I'm going to say uint n, and I will go with string value. And I'm actually going to change the type of this array to be a string array and show you how expensive this gets. Okay, now I will make this public. Now, what I want to do here is essentially initialize this array with n elements that are equal to this string value. Now, I need to remember to add my memory keyword, otherwise it's going to get mad at me. Okay, so let's do this. So what I'm going to do is write a for loop. I'm going to say for. Again, this will be I, uint I. This is going to be I is less than n. Let's add a space here, and then I plus plus. Okay, now what we'll do is say ARR dot push, and we're going to push the value like so. Okay, so right now we can technically run this infinite number of times, and I'll show you what happens if we try to do that, but I want to deploy this to our injected Web3 to the GoReli test network. So it says custom network right now. Let me just go to my MetaMask and change this to GoReli, and then we will deploy this and test it out. All right, so we are back on GoReli. I'm going to deploy. Let's see how much this is going to cost us right now. Okay, so not a significant amount of gas because obviously we haven't done any computation yet in the contract. And then once this is deployed, we'll actually try running this method and see how much gas it costs us. All right, so it looks as though the contract has been deployed. We can see it down here. It says create ARR. Now let's just see, again, this is going to be kind of anecdotal. I'll just go through a few examples here. How much it costs to do one that has 10 elements and the string hello world. Now I need to quote this string here, so let's do that. And let's transact and see approximately how much this costs us. So when I do this, notice we're getting 0.006876, okay? So we can kind of copy that and keep that in mind. And then I'll show you how this is gonna, I guess not exponentially, but go up a lot as I increase the value of n. So let's now do one that has 1,000 elements and see how much this costs. So when I do transact now, we're going to see that now we're at 0.05. Now, if you actually put that into the price of Ethereum, 0.05 Ethereum is a lot. Now, I'm not sure if it would be the exact same on the regular Ethereum network, but the point is you saw how we drastically increased this to a whole decimal point, right? Just by making this 1,000 instead of, say, 10. And then let's go crazy and let's make this something like 100,000 and transact and see how much this would cost. And here it tells me we actually cannot even send this amount of gas. The transaction will likely fail. So let's go to 10,000 and see if 10,000 is doable. Same thing, we can't even do 10,000. Let's try doing something like 5,000 and see if that's gonna work. Okay, 5,000 doesn't work. Let's try 25,000, transact. Okay, that's not gonna work. So just trying to show you here that we really cannot do a lot of looping operations. And even if we try to do a lot of looping operations, that is going to be very, very expensive to the point where it really doesn't make sense to do them inside of the smart contract. All right, so now that we've gone through those few examples, just so you can see kind of in the real world how much the gas is going to cost, let me delete all of this and show you that Remix can actually give us a gas estimate for specific functions. So what I can do is something like, let's go uint x is equal to 0, and let's go function set x. Let's take in a uint value. Let's just make this public. And then what we can do is say x is equal to value. Okay, so this is my function. Very, very simple. All we're doing is assigning a variable. Now, if I hover over the function name, notice that down here, kind of in the right corner, or I guess not really corner, but right on the console bar, it's showing us the execution cost is going to be 22,498 gas. So that's a significant amount of gas, considering we're only doing a very simple operation. All right, so now that we've seen that, let's just do a few more examples and estimate some more gas costs. So another thing we might want to do is evaluate a condition. Maybe we want to use a require statement or something like that. So let's just do something like require, and we'll say val is greater than, and let's just go with 10, and then we'll say val is too low. Okay, put our semicolon. Let's see how much gas it's telling us now. So if I hover over here, now you can see the gas has increased a small amount. So the require statement doesn't really use that much gas, right? Now let's see what happens if we try to add a number. So let's do something like x plus equals val multiplied by 10. And let's look at the gas estimate now. And notice it's giving us infinite gas. Now, whenever you're seeing infinite gas, that usually means that Remix is not able to estimate how much this is going to cost. Now, in this case, the reason it's saying infinite is because val can be any single number. Now, if val is any number greater than 10, when I multiply this by 10, Remix has no idea how much this computation is going to cost, because the larger value is, then, the more that this is going to be, the more gas this is going to cost, because the more addition operations we need to do. Essentially, whenever you're doing multiplication, you're really doing repeated addition. And well, the more repeated addition, the more gas this costs. So infinite gas is just telling you it could theoretically be anything. And you really want to try to limit these functions so that they cannot cost infinite gas. Because if they cost infinite gas, you could do a transaction that will never be able to run, because you can't pass enough gas to actually be able to execute it. All right, hopefully that makes a bit of sense. I just want to give you a quick example of the gas costs and how quickly they go up using smart contracts. Now I will talk to you about structs, and then we'll talk about some programs that are really limited on the blockchain because of the fact that we can't really do any looping, or at least not very efficiently. All right, so to illustrate structs to you, I first want to start by showing the alternative to structs, which would be actually representing objects using contracts. Now, contracts, just like classes, can be instantiated. So I can have different instances of the contract. Now, typically we just deploy a single contract, but this contract can instantiate another contract and then have a reference to them. So for example, I can do something like this. I can have contract person, I can have uint age, string name, uint balance, I can have a constructor, and then I can treat this just like I would any other class in, say, Java, right? Now, from this tutorial class, what I might do is create a function like this. And I might say function create and then person, and then maybe I take in my uint age and then my string memory name like that. And then the balance we would just imagine would be implemented at another time. Okay, then I'm going to say public. And then inside of here, what I can do is actually create an instance of this person class. So I would say person equals new person. And then I would just pass my constructor values. So this needs to be a string, sorry, age and name. Okay, there we go. I've just created a person instance. Now this is an instance of this contract. Now this looks perfectly fine. However, this is going to cost you a ton of gas because contracts are much more expensive to work with than structs. So instead, what you would want to do is replace this contract with a struct. Now the struct would look something like this. Let's do this, struct. And then we can remove the constructor and just do the following. Now, there's a few other changes I need to make here. So when I'm working with a struct, first of all, I no longer need the new keyword, and I also need to pass a balance, right? So I'm going to pass the balance 0. The reason I need the balance is because this is a required field in the struct. I'm storing an age, a name, and a balance. And if I initialize my struct in this way, then I need to pass all of these fields. I'll show you another way to initialize it in a second. Now we're getting an error. The error is that I need to specify the location for this type. The reason for that is this is a reference data type, meaning it's mutable, so I can change it later on. So I need to specify memory here, just like for my strings. Now, when I do this, notice it's all good. Now it's telling me I can make this a pure function, I believe. Yeah, because I'm not actually working with the state of the contract. This is just an example to illustrate the struct. Now I'm getting a warning here. It's just saying that this can be a pure function because, we're not dealing with the state of the contract. Anyways, this is what you want to do if you want to store like custom data essentially in a custom type, create a struct rather than creating a contract. So now to really kind of show the use case of a struct, we'll write a very simple contract that's going to allow us to associate an address with a person. So what I'm going to do is put a mapping up here, and I'm going to map an address to a person like that. Totally fine for me to do that, and I will just call this people. So now when I create my person, I will add them into the people mapping. So what I'll do after I make my person is I will say people at, and then this is going to be the address. So message.sender is equal to person like that. And then of course I would adjust the balance if money was sent into this contract. So now that we've seen this, I'll just show you another way of initializing this person because we don't have to do it in this way. So I can actually remove kind of the literal, I guess, written person and just say person, memory person like that. And now I can just specify the attributes on this person. So I can say person.age is equal to age. I can say person.name is equal to name. And then if I don't do anything for the balance, that's completely fine because the balance will be initialized as 0. Anyways, that's another way that you can initialize a struct. Just wanted to show you can do it in this way, or you can actually write out kind of, I guess, the main initialization or the constructor initialization where you pass in those values. Anyways, that is pretty much all I had for this first section here. I showed you the gas costs associated with looping and how looping is really a big problem in smart contracts and is unfeasible, especially if you're doing a large amount of computations. I also showed you that storing strings and bytes is very expensive and you don't want to do that. Lastly, I talked about structs here and how if you want to represent kind of a custom object or a custom type, it's much cheaper and better practice to use a struct rather than to use a separate contract, right? Which would kind of act as a class. You don't really want to be doing that in Solidity. There are some use cases, but if we're going to be creating a ton of different people like this, we definitely don't want to be using a separate contract. Now what I would like to do is really focus more on the limitations of Solidity based on some of these things you just saw and talk about how we would implement something like an order book in Solidity. Now, an order book is essentially what's used when you're trading stocks, you're trading assets of some sort. You want to have buy orders and sell orders and match the buy and the sell orders. Now, in cryptocurrency, you definitely need this. You need a way to exchange your different coins, buy coins, sell coins, whatever it may be. So I'm going to hop over to the Blackboard now, or the drawing tablet, and start talking to you about how we would implement order book in Solidity, a lot of the problems that we're going to run into doing that, and then some of the solutions we may have to actually make this more feasible. All right, so I'm here on my drawing tablet, and I want to begin by explaining to you what an order book is. So an order book is essentially used whenever you're trying to trade something. So in this situation, let's say we're talking about US dollars and then something like Ethereum. Now, an order book just really states the buy and the sell orders for this specific asset. So in this case, with US dollars, we would be buying Ethereum, so these would be our buy orders, and then on the other side, we would have sell orders. Now, whenever we want to actually make a trade, we need to match buy and sell orders together based on the price. So when I put in a buy order, I need to specify the price that I want to purchase Ethereum at. Now, what I would do is something like 1 Ethereum, and then I want to buy this at maybe 4K, right? That's the price that I'm willing to buy this at. I put that buy order into the book. Now, maybe someone wants to sell Ethereum. Maybe they're selling 1 Ethereum, and maybe they want to sell it at like 4.4 thousand. Well, if this is the case, we cannot match these two orders together because they have different prices. Now, you can probably realize just by looking at this, it's going to be very difficult to actually match buy and sell orders because the probability that two people are going to have the exact same price in mind for this specific asset, well, that's just very rare. You know, the seller is always going to want to sell high, the buyer is always going to want to buy low. So because of this situation, we can use multiple buy orders or multiple sell orders to fill either order, right? So maybe I have a ton of small buy orders, something like 0.1 Ethereum. Well, if all of these small orders allow me to actually fill one large sell order, then I would use, all, let's say 10 of these to fill this 1 Ethereum order. Now, of course, they have to be at the same price, and so we end up running into the same problem again. Now, this is where we talk about something called market makers. So I'm going to draw this right here, market maker. Now, a market maker essentially provides liquidity to this trading pair or to this order book because, as I was saying, it's going to be very rare to have our buyers and sellers agreeing on a price. So the market maker is actually a neutral entity that's always willing to buy and always willing to sell. Now, they have incentives to do this. They will earn some rewards, some fees, whatever it may be. But the idea is they're always buying and they're always selling. And this allows liquidity in this market. They make the market. It allows me at any point in time to go and buy my Ethereum or sell the Ethereum. Now, the market maker is pretty well dictating the price of this asset based on the pressure to buy and the pressure to sell. Now, I don't want to get more into this because it's a bit beyond my scope of knowledge and finance and all of that. But that's the basics of an order book. And now we'll talk about how you would implement something like that on the blockchain. So, of course, an order book is pretty important, especially when we're talking about cryptocurrency. People want to buy and people want to sell. So let's draw out another order book right here. And I'll talk about how we would actually kind of do this algorithmically. Because, of course, although this was done manually in the old days, we now have computers that do this for us, and they can do it very, very quickly and efficiently. So let's say we have a bunch of buy orders over here in green. We have a bunch of sell orders here in red. Well, the first thing that we should realize is that since we're going to implement this as a smart contract, if someone is going to be making, say, a large sell order, maybe of 1 Ethereum or maybe a lot more than 1 Ethereum, they're going to have to use usually multiple buy orders to fill this sell order. So they may have to actually loop maybe 20, 30, 40, maybe 500 times to actually fill their order. And as we saw previously, looping is very, very expensive. And so the more looping we have to do, the more it's going to cost whoever's performing the transaction. Now, we also may run into a problem where someone needs to loop more times than is allowed in the smart contract based on the gas limit. Let's say I want to make a sell order of maybe 100 Ethereum. Well, the chances that someone else is going to be buying 100 Ethereum is slim. Maybe there's a ton of people buying a small amount of Ethereum. So I might have to loop, say, 2,000 times. Now, if the maximum number of loops I can do in one iteration of my smart contract or one call, of my smart contract is 100, then I'm going to have to split this into 2 separate orders to be able to actually make this sell, right? I'm going to have to do 2 50th sells because I can only do 1,000 loops in one smart contract transaction. So that's kind of the main problem we're going to run into here, and it really just has to do with the ability of looping with the smart contract. Now, this is kind of a naive perspective because this assumes that everyone interacting with this contract is interacting with good intentions. They are a good actor. Everyone wants to buy, everyone wants to sell. They're not trying to manipulate the market. But of course, people are always going to try to manipulate the market. And one way they could do that with something like this is they could put in a ton of tiny buy orders. So let's say we have some buyer who's really trying to kind of lag the smart contract and make it take a very long time or be very expensive to interact with. Well, the way they would do this is they would put in a ton of fractional kind of bogus buy orders, and they would do this many, many times. Let's say maybe they have 1,000 of these orders. Realistically, it would be way more than that, but they have a ton of these orders that they're adding. They're all very small buy orders. Well, now, even if I want to make a relatively small sell order of, say, 1 Ethereum, I have to loop thousands of times, in this case, probably hundreds of thousands of times, to actually be able to fill this order because there's so many small buy orders. So now, again, that requires me as the seller to split this into very, very small amounts to be selling. So maybe I have to sell this amount at a time because I just cannot do enough loops in my smart contract transaction. So that's kind of a main problem that can arise here. You can have people try to manipulate the market, and when someone does this, if we're not handling this correctly, it's going to cause the seller practically to not be able to sell because it's going to take them so long, and it's going to cost them a lot of money to do that. So the way that we de-incentivize this type of behavior is we put the burden of looping on the buyer. Now, the seller is still going to have to loop to fill their order, but we try to make it so that less small buy orders come in by kind of penalizing those. So for example, if we want to purchase 1 Ethereum, what we do as the seller is we loop through buy orders, hopefully in an efficient manner, and we mark all of the orders that we require to fill this sell order as executed. Now, when we mark them as executed, that essentially means that we've made the trade. So we immediately take all of the USD funds, we give those to the seller, but then we lock this asset in the smart contract, and we require that the buyer do as many transactions as they originally did to buy to be able to take their stock back. So what I mean by that is if they did 1,000 of these tiny little transactions, they need to do 1,000 more transactions to retrieve all of those funds from the smart contract. So for example, if they want to take whatever it is they bought for, 0.0001 USD or ETH or whatever it's going to be, then they need to do one transaction, and that will give them whatever the amount of stock that was traded in this specific trade. Hopefully that's making a bit of sense, but they will take this amount of Ethereum, they'll get that from this one transaction, then they have to do this 1,000 more times because they had so many orders. So for every order, they need to do one transaction to retrieve all of the funds that were traded in that specific order. So this now puts the burden of looping on the buyer and hopefully de-incentivizes them from doing this. Now, of course, we still have this underlying problem that the seller needs to do looping to be able to actually fill their sell order. So we need to come up with an efficient way to do this, and that's what I want to talk to you about now as we head over to the other screen. So to reiterate here, the main problem that we're running into is that we're requiring a ton of loops to be able to perform buy and sell orders. And even if we implement that previous solution we talked about, the seller still needs to determine which buy orders to match with to be able to make the sale, right? And then we have to mark orders as executed. We have to store these orders somewhere. How do we do all of that? That's really the question right now. And how do we do it in an efficient manner? Because we can't have nested for loops. We can't have any crazy algorithms that are taking really long time to run. That's just not feasible on the blockchain and with smart contracts. Now, solution one is really the approach that has to be done on the blockchain, and this is to come up with the most efficient data structures and algorithms possible to implement what we just talked about. We need probably an advanced type of tree that's going to allow us to look for the largest possible orders to fill the largest sell orders, so we only use 4, 5, 6 orders and require a very little amount of looping to be able to make a sale. Now, of course, the same thing happens on the buy side. The idea, though, is that we need to do all of this efficiently. And again, we need to manage our storage efficiently as well because it's expensive to store orders on the blockchain. So solution one is essentially be a genius and come up with a great data structure and algorithm that has no bugs, has no problems, is never going to be inefficient, and use that. Now, of course, that's not really the most reasonable approach. Ask me to implement order book. I have no idea where to even start. That's going to be very complicated. I'm going to have to do a ton of research. Hopefully, I'm going to find someone who's done something like this before and kind of copy what they have. But even then, again, this is just really an impractical approach for most people trying to implement something like this. And even if you do come up with an implementation, the first approach is most likely going to be buggy, it's going to be inefficient, and it's probably going to be infeasible to use. So then solution two is essentially kind of similar to solution one. Copy someone else who's already done this. Hope that there's some genius out there who's written a great order book. Just take the exact same order book, maybe modify it a little bit if you were trying to make your own, and use that. Now, again, that's really still not a great approach. You can still have a lot of inefficiencies, and you still might have to loop a ton of times to be able to fill a buy or sell order. Now, the third solution is kind of more of an abstract one, but this would be to use something off the blockchain, maybe like a SQL database that's already very efficient at searching for specific orders. Maybe you write some advanced select query that can kind of give this information to you, and then you store hashes of this on the blockchain, whatever it's going to be. Unfortunately, interacting with SQL from the blockchain isn't really possible right now. At least I don't know how to do that, and so that kind of limits that option as well. So even with the only feasible option, which is essentially have a really good data structure and algorithm, you're still running into problems. Now, you might be asking yourself at this point in time, well, how is this done then? How do people do this if this is such a problem? Now, you can still use an order book. It's just not going to be the most efficient thing in the world. But what a lot of platforms are doing now is using something called a liquidity pool. Now, a liquidity pool has its own issues. I'm not going to talk about those in this video. Essentially, a liquidity pool is just a store of a ton of the assets that you're going to be trading. So you have whatever asset one is and asset two, you have usually an equal amount of them in the pool. And then based on the demand for the specific assets, the price of those assets will fluctuate within the liquidity pool. And the people providing liquidity, so putting their assets into the pool, will be given a type of reward, kind of like a fee that you would pay when you're actually trading them, right? Anyways, that's the liquidity pool. Again, has its own issues, but that's kind of an approach that's being used currently. And really, with that said, I think I'm going to wrap up the video here. Now, I know I didn't talk too much about the solutions, but that's because this video is really focused on the limitations of the blockchain and showing you that a lot of stuff we would like to be able to create that would be way simpler to do off the blockchain, we just can't feasibly do using smart contracts and on the blockchain because of those limitations. Now, even the stuff I showed you at the beginning of the video, strings, arrays, for loops, while loops, those are very inefficient to use. They cost a lot of money. And the reason we left them until the very end was because we don't really want to encourage their use. And I want to make sure that you understand kind of the problems with them and that they do exist. You can use them, but you should be very careful when you're implementing those specific features. Alright, so with that said, I am going to end the video here. Another massive thank you to Cartesi for sponsoring this video and this series. In the next video, we'll be looking at specific solutions and how we can actually write scalable smart contracts in decentralized applications. I hope you guys enjoyed. If you did, make sure to leave a like, subscribe to the channel, and I will see you in another one. Hello everybody, and welcome to the sixth and final video in this Blockchain for Beginners tutorial series. In this video, I'm going to talk to you about Ethereum scaling solutions, specifically solutions on Layer 1 and on Layer 2. And of course, I'll describe what Layer 1 and Layer 2 mean. Now, the reason we need Ethereum scaling solutions is because, as you've seen through this series, Ethereum can be quite slow, and the number of transactions that it can handle per second is very, very small. Now, this means it takes a really long time for us to actually submit a transaction to the blockchain and have that processed and validated. And if we want to be using a smart contract to perform computations, that can take a really long time as well, or be infeasible based on the amount of, say, iterations we need to do within a for loop or something along those lines. So there's tons of reasons why we need better scalability on Ethereum, and fortunately there's many different solutions. So with that said, we'll go ahead and get into the video, but I do want to thank Cartesi for sponsoring this video and this series. They're an awesome company that have been helping me come up with all of the content for this series, and they're actually working on a bunch of Layer 2 blockchain solutions right now and trying to make the blockchain more accessible and scalable for developers. So definitely check them out from the link in the description. They have a ton of detailed articles on a lot of the stuff I'm going to go over in this video, and I do just want to quickly mention here in the intro that this is going to be very high level. I'm not going to get into a ton of technical explanations about these different solutions. I just want to give you an introduction to them and then encourage you to research and learn more. Anyways, let's start talking about the difference between Layer 1 and Layer 2 solutions. So in blockchain world and in this video, you're going to see the terms Layer 1 and Layer 2 a lot. Now, Layer 1 is referring to the blockchain network itself, so the actual Ethereum main network, and Layer 2 is referring to stuff built on top of that network. So when we talk about increasing the scalability of Ethereum, when we're referring to Layer 1, we're talking about actually modifying the underlying blockchain technology, so changing the architecture, increasing the block size, decreasing the block size. Whatever the solution is going to be, it's going to be right on Ethereum, and that's something that we can't really directly modify ourselves. The people that are working on Ethereum would have to actually change. Then we have Layer 2. Layer 2 is referring to solutions we build on top of the blockchain. So we're not touching Layer 1, we're not modifying the Ethereum network, we're doing stuff on top of this to increase the scalability. So of course I'll get into those different solutions, but again, on Layer 2, we're relying on Layer 1 to give us the security and aspects of the blockchain, but we're not actually going to be modifying that underlying technology and that underlying architecture. Hopefully that is clear. Now what I want to do is talk to you about something known as the scalability trilemma, which has to do with the different aspects of a blockchain that we want to have and that we need to consider when we're picking different blockchain solutions. So the scalability trilemma is essentially a triangle. I'll put a photo up on the screen where each vertex or point is one of the properties or aspects of a blockchain that we'd like to have. So here we have security, decentralization, and scalability. Now, broadly speaking, what this says is that whenever we implement a solution, we end up lacking in one of the areas of this triangle, so one of these points. For example, if we implement a solution that has great security and great decentralization, typically we're going to have worse scalability. Or if we implement something with great scalability and great security, we may have worse decentralization. Now, this is not always the case. There is some solutions that are great in all three of these areas, but this is something that we want to think about when we're actually talking about different blockchain solutions. So does this increase decentralization? Does it decrease decentralization? What are the pros and the cons and the trade-offs as it relates to the scalability trilemma? Now, before we go any further, I do really want to define scalability as well as security and decentralization just to make sure we know those terms. So when we're talking about scalability, the common thing to refer to as it relates to blockchains is transactions per second or transaction throughput. Now, that is one of the areas of scalability that we're concerned with, but we're also concerned with data scalability as well as computation scalability. So when we were building smart contracts, one of the big issues there was we don't want to store a ton of data, and we can't do too many computations in the smart contract because of the cost on the Ethereum network and the time it takes to actually process those. So keep that in mind as we go through this video. It's not just the number of transactions, it's also computations and data on the blockchain. Now, as we go to decentralization, that's really referring to the centralization of power, or in this case, the lack of centralization of power. So the example I always like to use is a bank. A bank is an example of a central institution or organization. They have, a few executives or a few board members that really control what the bank can do. They have investors, they have government interests, whatever. It's very, very centralized. The people that use a bank don't control what the bank is able to do and what control they have of your money. It's the bank itself, very central, that controls all of that. So hopefully that makes a bit of sense. Now, when we talk about blockchain, we want everything to be decentralized. So there's not one person, one institution, or maybe a few people or few institutions that have control over the network. Ideally, we want millions of computers or thousands of computers around the world to be running and securing this network so we're less prone to hacks, less prone to corruption, and all of those other things that can happen when you have central power and central, authority of something. So hopefully that makes a little bit of sense. Then we're talking about security. This is pretty straightforward, but how secure is the network? How easy is it to be hacked? How sure can we be that this transaction is valid when it's posted on the blockchain ledger? All of those types of things relate to security. All right, so that is the scalability trilemma. Keep this in mind as we go through the rest of this video. Now I'm going to start talking to you about layer 1 solutions. Now I'm not going to spend too much time here because we don't have much control over layer 1 solutions. We can't really build a layer 1 solution because we don't have control of the Ethereum network. Regardless, though, I will talk about why we would want a layer 1 solution. So why would we actually want to improve Ethereum? Well, as I'm sure many of you are aware, Ethereum is relatively slow. So when we're talking about scalability, it only does about 15 transactions per second. And in contrast to something like Visa that can do upwards of about 60,000, that's really, really slow. And that makes it infeasible for a ton of different applications, especially something like being the global currency, right? If we wanted everyone to be using Ethereum for their day-to-day transactions, well, that would take a really long time because we would have to be waiting hours, maybe even days for a transaction to go through because we can only do 15 per second. Now, in terms of computations as well, we've seen when we were working with smart contracts, we're really limited in what computations we can do. We probably can't implement any advanced data structures and algorithms, we can't store too much information, and we can't do too many iterations without it costing us a ton of money on the blockchain. So that is kind of the reason we would want to improve Ethereum because of those lack of scalability issues. Now, Ethereum is very decentralized and is very secure, so we're not super concerned with those two aspects. We just really want the scalability to increase without hurting the decentralization and hurting the security. Anyways, let's talk about the layer 1 solutions. So currently, Ethereum is actually working on a layer 1 solution, which they're calling Ethereum 2.0. This is going to be a complete change to the architecture and the algorithm used for Ethereum. So I'm sure many of you have heard of this before. They've been working on it for a really long time and it should be out relatively soon, but they're going to be changing from proof of work to proof of stake. Now, I'm not going to discuss the differences here or get into kind of a debate about which is better, but that is what they're doing. They're changing the main algorithm from proof of work to proof of stake, and ideally, they're going to be bringing the transaction throughput from about 15 transactions per second to upwards of 100,000 transactions per second. Now, I cannot confirm this. These are just the rumors and what I've heard online and seen when looking at the project. Anyways, that is kind of what they're doing. Now, in Ethereum 2.0, they're doing a few other things. One of the main things that they're adding is something called sharding. So sharding is really this process of taking a large piece of data and splitting it horizontally into smaller pieces of data, which can be handled by multiple computers at the exact same time. So to put this simply, imagine I have one piece of data, and this piece of data can only be processed by one computer at a time. Well, it's going to be slower to process that data than if I split this data into, say, 64 chunks or 120 chunks or whatever the number of chunks is going to be, and allow 120 computers, 2,000 computers, whatever the number is, to process these smaller pieces of data at the exact same time. So that's exactly what Ethereum is aiming to do. Take the large piece of data, split it into multiple smaller pieces of data, and then allow for parallel processing and to drastically increase the number of transactions per second. In fact, this is a similar thing that many large companies do and many large databases do to increase the efficiency or increase the scalability of their systems. So this is not just something that's done in blockchain. This is done generally in computer science, and I would encourage you to read more about it and look it up if you're interested in exactly how sharding works. Works. So with that said, that's going to wrap up our layer 1 solutions. Now I'm going to talk about the layer 2 solutions. So as a reminder, layer 2 solutions are simply solutions built on top of Ethereum. So they rely on the Ethereum network and they do not modify it, and they aim to increase the scalability while again still keeping the decentralization and security aspect. So with that said, let's talk about some different layer 2 solutions. Now the solutions that we have are things like state channels, side chains, and then rollups. Now I'm actually going to start with side chains, so I probably should have listed it in the other order. But what a side chain is essentially another blockchain network that has a different architecture than the Ethereum network and makes it better for scalability. So what a sidechain actually does is it links to the Ethereum main network and makes it very easy to transfer assets between the two different chains. Now, typically sidechains are going to be much smaller, they're going to have less validators, they may have smaller block sizes, and this does actually decrease the security and the decentralization of the sidechain, but it drastically increases the scalability because now, rather than me sending a transaction to Ethereum, I'm going to send it to a sidechain, and then the sidechain can kind of link up with the Ethereum main network and allow me to transfer the assets between the two networks very, very quickly, or very easily at minimum. So an example of a sidechain would be something like Polygon. I'll put up an image on the screen. These are controversial, and there's a lot of reasons why you may not want to use a sidechain. But again, the basic reasoning here is rather than using the Ethereum network, we're going to use a completely, entirely different blockchain network that's going to be somewhat linked to the Ethereum main network, which allows us to take the smart contracts running on the sidechain and very easily port them over to the Ethereum main network while still maintaining all of the data, all of the assets, and all of the information essentially that was posted to the sidechain network. Hopefully that makes a bit of sense, but those are sidechains. So the next solution that I'm going to introduce to you is something known as state channels. Now, I just want to emphasize before doing that, again, I'm bringing this to you at a very, very high level. There's a lot of details and nuance with all of these solutions, and you really should do some research and look at these more before actually trying to implement them or use them for your decentralized applications. So please keep that in mind. This is a very, very general introduction. Anyways, state channels. To explain the usefulness of state channels, I want to introduce to you a problem of making a decentralized application. So if we wanted to make a decentralized app, we want this to be some type of game, maybe a game like chess, right? Well, this game requires many state changes. Now, we know when we make a decentralized application, we're going to have a smart contract. The smart contract handles the state of our application. If we're talking about chess, it would need to store the state of the board. So if we want to play a game of chess on the Ethereum network, what we would have to do is send transactions to the smart contract to update the state after every single move was played. Now, at least in the chess games that I play, they're like 5 minutes long or 3 minutes long, and we make moves every few seconds, right? So I make a move, my opponent makes a move, and every time that would happen, if we were running this on Ethereum, we would need to submit a transaction to the network. However, the next player can't make a move until that transaction is verified and the state has been updated in the smart contract. And we know that that can take a really long time to happen, so that makes it infeasible for us to play a game that has very rapid state changes. Hopefully that makes sense, but you would be sitting there waiting 30 minutes, an hour for the transaction to be finalized before the next player would be able to move, and well, that completely defeats the purpose of like a quick game of chess or something along those lines. So this is where we introduce state channels. So the idea here between state channels is that if we have a ton of microtransactions or many transactions that are going to be occurring in a short period of time, rather than doing them on the blockchain, we're going to take them off the blockchain and do them in a secure way that can later be verified by the blockchain. So a state channel is essentially a communication channel, a peer-to-peer messaging channel, where me and someone else who are participating in, for example, some type of game, are going to be sending signed messages to and from each other with the state of the game. So if we're playing a game of chess, I'm going to be sending a message that's signed by me to my opponent saying, I made this move. And then they're going to send me a message that's signed and said, I made this move. And we're both going to be verifying that the state is correct at each point in time by signing these messages. Hopefully that makes a bit of sense. Now, the way that this works is we're first going to send a transaction to a smart contract sitting on layer 1 to open up the state channel. Once the state channel has been opened, we're going to do all of our transactions, the micro quick ones, off the blockchain. They will happen almost instantly. Then at the end of the game, we're going to send one transaction to the smart contract with the final state. And we're going to say, hey, we finished the game. And then the smart contract is essentially going to verify that the state is correct. And there's a lot of stuff that goes on to do that. I won't really talk about how that works. And if we were playing for, say, 1 Ethereum, so whoever wins the chess game gets 1 Ethereum, then that Ethereum would be transferred, and we would have had to kind of stake that at the beginning of the game. So hopefully that makes a bit of sense, but typically state channels allow for us to have very fast transactions. They make it very cheap because we don't have to pay gas fees when we're doing this off the blockchain. We just have that first and last transaction that require the gas fee to open the state channel and to close the state channel. And typically they do allow for the same security and decentralization. However, you may have the security be slightly decreased depending on the way that you're verifying the states and what you're doing between the blockchain and the off-chain, or between layer 1 and layer 2. Again, I don't want to get into this too much. Those are state channels, very useful when you have a ton of microtransactions that need to be performed very, very quickly. So now we are moving on to the final solution I have in this video, which is rollups. Now, before I get into those, I do want to mention that Cartesi actually implements a ton of layer 2 solutions and makes it really easy for developers like yourself to use these solutions without having a full understanding of how they work and what's going on behind the scenes. Cartesi is working on operating systems, libraries, modules, packages, frameworks, all of the stuff you could imagine is going to make it easier for you as a developer to use these types of solutions that are really complicated on a lower level. So make sure you check them out from the link in the description. Anyways, let me talk about rollups here, and I will also mention that Cartesi has a ton of articles that explain this stuff more in depth. If you're interested, again, reference them from the link in the description. So a rollup is essentially an idea that we're going to take all of the transaction execution, so the computations associated with the transaction, and perform those off the blockchain while posting transaction data to the blockchain on layer 1. So the basic concept behind rollups is that it's very expensive to perform computations on the blockchain. It can also be very time consuming. So rather than do them on the blockchain, let's perform our transaction execution off of the blockchain and then post the transaction data to layer 1 and have a smart contract on layer 1, so on the blockchain, that can validate that the execution that we did off the blockchain was indeed correct. Now, I know that's confusing, but essentially we're taking the time-consuming operations and computations, performing them off the blockchain, and then posting all of the data to the blockchain, where we can then validate that it is correct, and we can use the properties of the blockchain to store the data. Now, another advantage of the rollups is that what they can do is they can bundle multiple transactions, so maybe hundreds or thousands of transactions, into one smaller transaction, and then post that to layer 1. So rather than having the user have to send 1,000 transactions directly to a smart contract, which costs a lot, takes a lot of time, we're going to send it to whatever's rolling up these transactions. It's going to kind of bundle them all together and then send one transaction to the blockchain that contains all of the data that it needs, or the state change that's going to be made. So before I can go any further, because I do want to give you some more detail here, I will mention that there's some different types of rollups. So we have optimistic rollups and pessimistic rollups. Now I'm going to start with optimistic rollups. Now I do want to add here that the blockchain community currently considers rollups to be one of the most promising solutions for scaling Ethereum, and the reason for that is that they allow you to scale the computations and throughput of the network without compromising on security and decentralization. So using that in combination with sharding, which allows you to scale the data on the network, really gives you the best of both worlds and allows you to scale Ethereum in all three of the areas that we talked about. So sharding scales the data, and the rollups allow us to scale the computations as well as the throughput, so the transactions per second. So you're likely going to be hearing a lot more about rollups in the future, and maybe even using them yourself. And if you were to pay attention to any of the solutions in this video, this would be the one that I recommend. So when we talk about optimistic rollups, what we're really referring to is that the smart contract that's sitting on layer 1 is assuming that any of the transactions sent to it are valid. So any of the state changes that are made, any of the transaction data, we just assume that's valid and that it's not malicious. Now, this allows for us to have very quick transactions and to perform faster computations off the blockchain because we don't have to prove that everything is correct. However, this does mean that someone could submit a malicious transaction. Now, there is incentives put in place to make sure that people do not submit malicious transactions. For example, there may be something like staking Ethereum. So whenever people are dealing with rollups, you may have to stake some Ethereum that says, hey, I'm going to be a good actor. I'm not going to submit any malicious transactions or state data. And if you do that, so if you are malicious, your stake could get slashed. That could be the incentive or de-incentive from performing poorly or having bad behavior on the network. Hopefully that makes a bit of sense. But the idea here is that we're assuming everything is correct. Now, if someone does do something that is not correct or is invalid or malicious or whatever, anyone can submit something known as a fraud proof. Now, this fraud proof essentially says, I believe that this state is incorrect. I believe that someone did something malicious. Go and verify that it's not, or go and verify that they did indeed do something malicious. So that's what it's called. It's a fraud proof. This puts the smart contract into a specific mode where it's going to go and validate that all of the transactions and data that are sent is actually correct. And if they are not correct, it's going to punish whoever submitted the incorrect transaction. Hopefully that makes a bit of sense, but that is optimistic rollups. Again, just really think about the fact that an optimistic rollup is assuming everything is correct, and it's only doing a validation if someone submits a fraud proof. All right, moving on now to pessimistic rollups. Now, pessimistic rollups are kind of the opposite of optimistic rollups. In a pessimistic rollup, you cannot submit or update the state of a smart contract unless you submit something known as a validity proof. Now, this proof is a specific cryptographic proof. I'm not going to really talk about exactly how it works, but essentially off the blockchain, when you're performing all of your computations, you also need to compute this proof, and then this proof is sent to the smart contract. And you can only submit or update the state, of the smart contract if you have this proof alongside it. Now, the only real issue with these type of proofs, though, is that they can be inviolable to compute for really complex transactions. So these are time consuming and difficult for a computer to come up with, these cryptographic proofs. And so if you're doing anything that's too complex, it can be inviolable to come up with one of these proofs. And in that situation, you need to use an optimistic rollup. Now, the reason you would use one of these proofs, though, is because this limits the amount of data that the smart contract needs to hold, because all it needs to do is hold a state, because it can only update the state if it has a valid proof. I understand it's a little bit confusing, but in the optimistic rollup scenario, it's holding all of the transaction data, and it's only doing a verification when a fraud proof is sent. So it is time consuming when you send the fraud proof, but ideally you're not having that happen very often. Whereas in a pessimistic scenario here, the smart contract is holding much less data. It's just storing the state, and it's only updating that state when you submit the proof. This means it's really easy for the smart contract to validate that everything is correct. However, it takes more time off the blockchain to be able to submit these state changes because you need to perform this validity proof, and sometimes this validity proof can be inviolable to compute. All right, so that's pretty much all I can share with you related to rollups, without getting into too much detail. Again, I want to emphasize this at a very high level. There's a ton of stuff that I skipped over and omitted in this video. With that said, I'm going to start wrapping it up here. Another massive thank you to Cartesi for sponsoring this video and this series. Make sure you check them out from the link in the description. They have all kinds of articles, very smart people there that are implementing these types of layer 2 solutions and are trying to make it much easier for you and me to develop decentralized applications without the huge issues or limitations of Ethereum that we looked at in some previous videos. I hope you guys enjoyed this series. If you did, make sure you leave a like, subscribe to the channel. Please leave a comment down below and let me know if you want to see more blockchain on this channel, because I'm hoping to do some more series in the future. And with that said, I will see you in another YouTube video.